Friends, today we are going to learn about photogrammetry. Please ensure that they are connected. Hello, good morning once again. Good morning. Good morning, all the centers connected today.
Good morning.
Hello, good morning, sir.
Good morning. Good morning, please. If you're all connected, we can start.
Got connected.
Okay. All connected? Okay. So friends, today we are going to discuss about photogrammetry. I consider this lecture to be an elementary ABC about photogrammetry. But I hope that this will help you to understand the different aspects of photogrammetry. Yesterday in my lecture, I told you about the remote sensing, and my focus was how significant it is to use the aerial photographs or the satellite imageries. And I told you that when we look at the photographs, we immediately get information and we feel that we are in a position to extract information. So in the afternoon session yesterday, one of my students and colleague now told you about the data extraction from the satellite imageries and the photograph. I hope you must have enjoyed that session. Friends, now when it comes to extraction of the information, before that we have to understand some basics of photogrammetry. Now if you look at the definition part of it itself, now what we find that photogrammetry is the science of making measurements from photographs. So while it is very easy for us to see objects, detect objects, identify objects on the photograph, now most of us finish our activities there itself. But the problem lies beyond it. And when we want to do measurements on the photograph, many beginners do not know how to do the measurements on the photograph. So it is easy to see the objects, but it becomes very cumbersome and difficult to comprehend the measurement part of it. So photogrammetry is the method of obtaining reliable information about the properties of surfaces and objects without physical contact with the objects, and of measuring and interpreting this information. Now, so what happens when we have taken the photograph? We bring the objects of nature in our laboratory. Now the entire measurement will be done in the laboratory. Now we do not carry any dumpable or theodolite with us in the lab. Rather, we have brought the natural landscape inside the laboratory, and we are doing it at our layer without any physical stress on our body. And that is a big advantage. That means all the landscapes, all the features can be seen in the lab, and now you have a freedom to see it as and when you want to see it. Rather than when you do it in the field, you have to go, and then if you want to see it again, you have to go again, and then you don't like to go. In case of photographs or satellite images, the entire lab has the facility where you can do your exercise very comfortably in an environment, and you can repeat your visualization as many times as possible. So it is a technique of measuring objects now in 2D as well as 3D. Now things have improved today that we have 3D movies also. At one point of time we had 2D movies, and now so we'll learn about it also. It is most important feature is the fact that objects are measured without being touched. So you're not touching a mountain, you're not touching even rope and anything else, and then things are measured. How do we do it? Let's look at. So if you look at the photogrammetry part of it, now I divide them in 4 important phases. The first phase was called as first generation phase, when we invented the photography. I told you yesterday that we started the photography way back in early 19th century, and then by 1900 this phase is called as first generation. So from the invention of photography to invention of airplane is one phase. Second phase, from the invention of airplane to invention of computer was the second phase, and that ends around 1950. And if you look at the third phase, which begins from 1950 and goes up to 2000, and this phase where you find that digital computers, the analytical part of it started. Now beyond 2000, that is in the last 16 years, a lot of things have been developed in case of photogrammetry, that now measurement is not required. The way we are doing manually, now they can be done in automation. Now this is a great advantage, but then while you do so, you have to understand the basics of the photogrammetry and look at it. Now the first part, which is very important and elementary, because whenever I teach the engineers, I have realized that most of our engineers, they are competent in their own field, but when it comes to the interpretation of photographs, they miss a very important part, and that is they have to distinguish first between a photograph and a map. Now if you look at the photographs, you find that the photographs have a particular projection. So you'll find them to be a central projection. I'll discuss them later on. Whereas if you look at the maps, they are orthogonal in nature. So if you look at the projections and if you look at the maps and photographs separately, you'll find that maps can be prepared on different projections. And when I say map projections, in simple school days, you must have learned that map projection is an art of transferring the spherical surface on a flat sheet of paper. So what you see on a map is a transformation of the spherical surface on a flat sheet of paper. But how do we do it is certainly a very scientific method. So for that, we apply different kinds of projections. So since the map projection is not the scope of today's lecture, I'll skip that. But when we look at the photographs, now photographs are prepared on a central projection. Now when I say central projection, you have to assume that we are using one single eye. So your camera has just one eye. Now here begins the question of simple mathematics. And simple mathematics says that we human beings use two eyes to see the objects. And now our camera has just one eye. Even satellites, when they take the images, there also we have one single eye. Now as a scientist, you question yourself that what will be having an impact when we see things with two eyes or when we see things with one eye. So you might have read in some of the books or in the newspapers that when we launch a satellite, we say that this is the third eye for the human beings. But then this third eye, he has just one single eye, and one single eye will have many limitations or many conceptual underpinnings which one has to understand. Now, so if you look at the photogrammetry, the purpose is to make accurate measurement. It is necessary to determine as accurately as possible what? Two things are very important. First, you have to understand the photographic scale. Now you must have seen your own photograph in your life many times, be it black and white of old days and colored now. But have you ever thought that can I measure my skull? Can I measure the size of my face? None of us ever thought about it, because we are happy just seeing our photograph. Because our mindset is that if we recognize persons on the photograph, we are happy with it. We don't go beyond it. But when it comes to photogrammetry, suppose you are a doctor and then you want to find out the size of cornea. Now here comes the measurement. For a doctor who is doing a surgery on eye, if he is not knowing the accurate measurement of your eye, the possibility is that he might make mistakes. And when it comes to surgery on eye, then we have to go for measurements in sub-millimeters, not even millimeters, sub-millimeters. So it requires very precision. So the first task before us is that we are aware of map scale, but then we hardly care or worry about the photo scale. But when it comes to scientific work, then we have to first develop a photo scale. And remember, friends, here that photo scale will be dependent on two factors. First, the focal length of your camera, which you normally adjust when you take the photographs. Number two, the distance from which you are taking. So two things are very important. First, the focal length of your camera. Second, the distance from which you are taking the photograph, because that determines and decides the photo scale. But how many of us really bother about any of these? We don't bother. What we bother? We bother about the quality of the photograph. And if the quality of photograph is good, we don't bother about the photo. We don't bother about the photo scale, or we don't bother about the focal length of the camera. We don't bother about the distance at what we are taking it. And number two, we have to understand the basics of projections. Both are very, very elementary, but very, very significant. So if you look at the maps, on one page of map, be it world map, be it India map, if you remember school days, you find that there was mentioned a scale. But the scale on this map was constant. So if you wanted to measure distances from place A to place B on any part of the map, the scale was constant. And in this map, there was no relief displacement. That means the relative location of objects with respect to each other was perfect on the map. But when you do the same exercise on a photo, what you find, scale varies with elevation. First is scale varies with elevation. Why? Because the distance of your camera and the object will change. Since the distance of the object and the camera changes, the photo scale will also change. Number two, there will be a huge amount of relief displacement, which I will discuss later on. But let me tell you that when we talk about a photograph, on the photograph, what will happen? Since it is in central projection, the outer part of the photograph will have a serious exaggeration in the scale, and the objects which will be displayed on the margin, they will be displaced because of this projection itself, which we will discuss later on. Maybe I need the board also to explain the facts. Friends, it is very important for us to understand the types of real photos. Now, broadly, we have vertical photographs and we have the oblique photographs, two broad categories of photographs. Now, the oblique photographs can be again divided into two parts, the high oblique and the low oblique, which I'll explain you with the help of diagrams. Now, as far as the vertical photograph is concerned, the camera axis is vertical. I'll explain with diagrams also. And then in this kind of vertical photos, 1 to 3 degree of vertical is acceptable. That is the average tilt on vertical photograph is there, then we accept it. But in case of high oblique, which we do it intentionally, so that we can, because our eyes are not accustomed to see objects from a vertical position. And for a simple example, that if in a group of 100 people sitting in any lawn or any hall, if you take their photographs from top, what will be visible? Only their heads will be visible. Now with the heads, it is difficult. With the heads, it is very difficult to identify and recognize people. So we say, yes, there are human beings, but which person is not possible. So if it is inclined or if it is tilted, then the faces are visible to us, and then we can say that this is this person, this is this person. So we normally go for the inclination also. Then we have low oblique photographs and high oblique. But when it comes to the measurement, friends, let me tell you that the vertical photographs are the most suitable and significant for the measurement purposes. Now, why vertical photographs? Now, a vertical photograph is taken with camera pointed as straight down as possible. Allowable tolerance is usually plus 3 degree plus minus from the perpendicular plumb line to the camera axis. The result is coincident with the camera axis. A vertical photograph has the following characteristics, which is very important for you to understand. I assume today that you have in your teaching must have used some aerial photographs. So the first characteristic is the lens axis is perpendicular to the surface of the earth. 2. It covers a relatively small area. Since it is a vertical photograph, it will cover a small area. 3rd, the shape of the ground area covered on a single vertical photo will be closely or approximately a square or a rectangle. 4th, being a view from above, it gives a unfamiliar view of the ground. And 5th, distance and directions may approach the accuracy of maps if taken over terrain, flat terrain. So if the area is flat, then the scale will not be that difficult. But if the area is not flat, then in that case, if it is hilly topography, scale is very important. And so relief is not readily apparent in case of vertical photograph. So if you want to appreciate whether it is a mountain, whether it is a valley, you won't be able to appreciate because things become in 2D format. So what we do? Suppose it is low oblique photograph. So what will happen? A low oblique has the following characteristics. It covers a relatively small area, but certainly more than the vertical. 2. The ground area covered will not be now square or rectangle, but it will be a trapezoid. Now on the photograph here it is a trade-off. Trade-off is that, see, whether it is a printed photograph in rectangular, so the page which you use may be rectangular in shape, square in shape, but the image which is projected will not be square or rectangular, but the image which will be covering an area which will be trapezoid in shape. 3rd, the objects have a more familiar view because now you can see the and you can recognize, comparable to viewing from the top of a high hill or tall building. No scale is applicable to the entire photograph, even if it is taken in the plane area. In case of vertical photograph, if the area is flat plane, then the scale is quite close to near correction, and distance cannot be measured. Parallel lines on the ground are not parallel on this photograph. Therefore, directions cannot be measured. I repeat, parallel lines on the ground are not parallel on this photograph. I'll demonstrate it on the board first. Friends, assume this is a photograph and this has been taken from a low oblique situation. Now look at it, what I'm going to draw here. So I find a road here. This is how a road will look to me on a photograph, because this is from a low angle. So one will get an idea that, okay, I am driving on this road, assume it. Not a very difficult. But now what I am going to do, I am going to do some measurement on this photograph. The moment I go for the measurement, on the photograph, I realize that when I put a simple scale for measurement, the distance at this point is not working. You don't have a good time. None of them is working. Okay. So what you find that the moment I go for measurement, I realize that the road sides which were supposed to be parallel, now they don't look parallel to me. What I find that now my mind and my eye, they are in conflict. My mind says that this is a parallel road. That means these sides of the roads are parallel. My mind says, because that is what I have seen in my life. But when I see the photograph and start doing measurement, I find that when I do the measurement of the photograph, I find that the distance here on my scale and the distance here on my scale will be different. And that gives me an idea that if my photograph is taken from a low oblique position, these kinds of error will automatically creep in. They'll creep in because when you do the measurement, your measurement will say that this part of the road is wider, this part of the road is narrower, but in real terms it is not. Now that has to be rectified only with the help of photogrammetry. I come back and move ahead. So relief is discernible but distorted. So in a low oblique photography, you can appreciate that it is mountainous area, it is a valley area. But in the low oblique photograph, you will not see the horizon because it is limited to a low degree. Now, when I say low oblique, what I mean the inclination of camera only. So plane will be in the air, camera is inclined, or camera is meant vertical or low or high oblique. So if it is high oblique, what will happen? The high oblique photograph is taken with an inclination of about 60 degrees. So you incline your camera by 60 degrees. Now what will happen? It is going to cover a large area. And of this large area, all part of the photograph is not usable. The ground area covered is again trapezoid in shape, but the photograph may be rectangular or square. That is how you print it. The view varies from the very familiar to unfamiliar. So maybe the objects which are far away from you may not be familiar to you and you can't identify them, depending on the height at which the photograph is taken. Distances and directions are not measured on this photograph for the same reason that they are not measured on the low oblique. So same problem is there here also. Relief may be quite discernible but distorted as in any oblique view. The relief is not apparent in a high altitude, high oblique. Why? Because some part of the mountains which are behind the other mountain may not be visible to you. The horizon is always visible, but on your photograph you will find in the background the horizon, which is the apparent feel of sky and earth meeting, though they meet never. Now look at the situation which I discussed with you, friends. So the first diagram shows the vertical position of the camera, and look at the shape. So we have vertical, and then the shape of the area which is covered is almost this rectangular or square. In the low oblique, you can see that the area which is covered is trapezoid in shape, but if you look at the high oblique situation, you find that the horizon is visible to you, and all the measurements which are to be done are not possible to do. But then one point is very important for us to understand, and here I'll again devote some time with you, because seeing a photograph is different thing, but working on the photograph is very different. And some principles which you have to understand. As a scientist, as an engineer, you will come across such a situation. I told you in the beginning that your camera is just one eye. Just one eye. Now the first point which is very important when we come to the measurement is that we have to create, friends, a situation with our natural vision. And when I say so what we do in the normal conditions, friends, in the normal conditions, look at what our eyes behave. So suppose this is an object. Now what happens, this part of my eye and this part of my eye, they both converge, and when they converge and see the same object, so how many eyes are required to see an object? Normally, suppose I have to see this pen. Now both my eyes, they converge. Okay. So it is very important that we can appreciate the third dimension of an object only when we see them with two different positions and then when they take convergence. This is how we see the objects in our daily life normally. We require two eyes to see the object, and there is a convergence point. Now, in case of photograph, what happens? Let's look at it. In case of photograph, we have one photograph, and this photograph was taken from one location. So this is our location. So here is our camera, and from this camera we see the object on the ground. Okay. Now only one eye is there. Only one eye, and I'm going to replicate this. So one point is very clear that see we normally we do like this, but when we take the photographs, what happens? Look at it. I'm going to draw a diagram for you, and that will make the things clear. So suppose this is my camera, and this is the ground surface. If you have any question, please note down, because in the end we can discuss them. But then learn it with an open mind. So look at the situation, friends. So here is our camera. This is our negative plane. This is our optical center. OC, optical center. Now the distance between the negative plane and the optical center will be called as focal length. I repeat for you. So this is the negative plane. This is the optical center, and the distance between negative plane and the optical center will be called as focal length, which we will discuss later on. What is the significance of focal length? Now, if you look at this situation, now what you find that in this case, our camera axis is vertical to the ground. This is called as the principal point, the PP, on the ground, and this will be called as PP dash on the negative plane, principal point. Look at this. Now this is the vertical photography. This is vertical photography, friends. Now the output of this photograph or photography will give you a photograph of this kind. Now this will be the photography for you. That means the area which you are going to cover will be of this kind, and of this photograph, if I put a dot here, now this dot will be the location, pointing out the position of camera vertically above an object. So this is my photograph. On this photograph, I locate the principal point. Simple principle of locating the principal point is that on every photograph, you will find your fiducial marks. We call them as fiducial marks. They might be of different types. Sometimes these marks are marked here itself, inside the photograph. Okay. Now, sometimes what you find, if you have to find out where was the camera vertically above an object in our area when the photograph was taken. So what you find, the camera was vertically above this object when the photograph was taken. Now, in order to locate it, what we have to do? We have to simply join this fiducial marks diagonally. So this and this point and this point, wherever they intersect, friends, we will come to know about the principal point. Now, this is the principal point of the photograph. Principal point is simply on the photograph is the position of the camera vertically above an object. So if this was an area, and when the plane was flying, maybe on this point there was a tank. So the tank was vertically below the camera. I repeat, the tank was vertically below the camera. So the tank is vertically below the camera, and that is the point which you can locate on the photograph, and that will be called as the principal point. Principal point. Now, if you look at it very carefully, what do you find? That this is the situation where we are. But then, in principle, what we find that this is one situation. We are observing this area from one particular position. But this is not what we ideally do in our daily life. What we do? So we have to replicate a model in the land by doing a very scientific exercise that can I replicate the way I see things in the nature? So what I do? I will change my position from this to a new position. to a new position. And now look at it, what I'm going to do. I move on. This is my plane is moving, and I come to a situation where my negative plane remains the same. Now look at this carefully. Now what you find that my camera has moved now from one position to another position. And here again we have the negative plane, we have the optical center. This is common in both cases. What has changed? The point of observation from this has changed to point of observation to this point. Which is shift. Position has changed. Why do we do so? Now from this point also we are going to see the same area. Can we do so? And then we find that no, our limit was here only, and this is a different area. So below us, what will happen? We will have a different area. So this area and this area are not same. I repeat for you, very important. What you see that when I change my position of the camera from this point to this point, I realize that see, this time my area is different, not the same area. But if you remember my previous slides, where I told you that when we see an object, same object is seen from two different points. Let me draw the diagram again for you. Normally what we do, we see the same object from two different points. So object is same. Here what happens? This area is different. This area is different. Now, but what I need to create a situation like this, where this eye see the same thing, this eye see the same thing. So what I've done? I've done a mistake here. Mistake is I have moved my camera far away, where I cannot see the same area from this point. So what I need to do? I have to readjust my camera in a manner that I do the photography from a closely spaced position. So now I do it from a different location. And look at what I'm going to do for you. This pen is not working properly. So this is my negative plane, and look at what I'm going to do now. Now friends, look at this photograph. So now what happens? Now look at it. Now the area coverage will be having a different situation. Now this is my new area. Now this is my new area. Now what I find that when I take photograph from this point, this was my area cover. When I take the photograph from this point, now the area covered is this one. But in between there is a very interesting thing. What I find that this area is common. This area is common. Now what I've done? I have done something very interesting. I have created a system like I situation. What it means? It means that I am now getting a view of this area, and this area is to be seen, and their common area. So I am now developing something in the laboratory where I see this area with this eye. I see the same area from the other location, and to do so, friends, I am supposed to have photographs taken which have an overlap, concept of overlap. So this photograph and this photograph, they will have a concept of overlap. So if you look at the diagram displayed on the screen, you can see that. That one, where the plane is there, let's look at it. Now what do you find here? That there is an overlap. There is an overlap, friends. Look at it very carefully. So the plane took the photograph for this area, the same plane moved, and then we find it is taking the photograph. But here we have a 60% of overlap, friends. This kind of overlap is called as forward overlap. This is called as forward overlap. And you can do measurements and you can see the third dimension of the object only when you have this situation. But how will you see it? You can see them only if you develop or if you have an instrument called as stereoscope. You have a stereoscope. Now I am going to draw a different diagram for you to make the things much more clear. This is very interesting. So friends, what we do, we develop a simple instrument called as pocket stereoscope. So we have one lens here, another lens here, and then these lenses. Need a good pen. Any other pen, first of all, throw all of them, okay? So that other person is really confused. Yes, this is better. Thank you. So this is better. So friends, look at it. What we do, we develop a simple stereoscope. Commonly in engineering colleges or in institutes, we call them as pocket stereoscope because this can be folded and kept in the pocket. No problem. So what we have one lens here, one lens here. And what I'm supposed to do? What I do that I place the photograph, one photograph here. I place the other photograph in a manner that I can see the overlap between them. Okay. So what I have such a situation. Now what will happen? Now if I'm looking the photograph with the help of this instrument, but I find that the amount of overlap, whatever is there. Now by this I see the object from this, and suppose the overlap is this much. Now by this I will see the object from this. So what I find that this overlap area is common in both the situations. Since I create a natural condition in the lab by having two different lenses, now what do you find? You find a difference. In our natural view, what happens? There is a convergence. We, in this case, what we are doing? We are artificially diverging our vision. Artificially diverging our vision. But then by doing so, what happens? My right eye see the same object, my left eye see the same object. Since the object is common, they will be fused as one in our brain. I repeat for you. The object is same, but I am training my eye to see the same object with left eye, same object with the right eye. Since the object is common, I create the same condition which I am trained since childhood to see the object by converging. But here is the divergence. So we have to train our brain for seeing the divergence. The moment the same image is before you, they are seeing from left eye differently, right eye differently, but the object is same. The convergence of this, the image which will be getting fused in your brain, and you can see the third dimension. This is called as stereoscopy. So friends, it is very important that when we are learning the photogrammetry, we have to understand the concept of stereoscopic view. Concept of stereoscopic view. Here it is very important for me to tell you that suppose you are heading an institution and you want to go for photography. It is very important that it is not a simple photography. Photography has to be done by keeping this concept in mind that there should be at least 60% of overlap in order to have the third dimension of the object. Because if the photography is done without this concept in mind, the entire photography will go waste. Similarly, friends, if we are going for satellite imageries, in our satellites, we have to suppose you are part of ISRO team. Now, ISRO team has a different work. Now, ISRO team will be providing all kinds of satellite launch provisions. But then their scientists will ask you, what is your requirement when it comes to imaging? So you have to explain that I want the images of this kind of resolution. I want my images of this kind of radiometric resolution. I want my images of this kind of temporal resolution. I want my images. Now all these instructions has to come from you, not from the ISRO people. ISRO people will be only providing you the launch of satellites, whether you want to launch a satellite in the polar orbit or whether you want to launch a satellite in the geostationary orbit. Beyond that, their capability is not. Now you are a remote sensing scientist. You have to tell your requirement, and you have to ensure that your requirement is supported by the available technology. If the available technology is not with you, ISRO scientists will not help, because they are trained in launch of satellite. So they know how to launch a satellite using a polar satellite launch vehicle. They know the technology how to launch a satellite in the geostationary orbit. So they have the GSLV. They know how to launch a satellite, but what kinds of equipments, what kinds of instruments, what kinds of recording these equipments are required, you have to explain them. Here you have to explain that we have to ensure a 60% overlap, which means what? When the aeroplane is moving, for example, in case of aerial photography, then you have to ensure that your camera keeps on taking photographs in a manner that it ensures 60% of overlap on all the consecutive photographs, minimum amount of this. So the forward overlap is to be taken. If the forward overlap is not taken, friends, the entire exercise will go waste. Similarly, in case of satellite images also, we have to ensure that when the images are prepared, the overlaps are ensured. Some of our satellites which we launched in initial years, in 88, they were not having the capability of this overlap. Now, when we are launching the satellites, we are ensuring that they have the facility of overlaps. Now, with these overlaps, friends, it is possible to view things in a much better manner. This is very important. Elementary, but very important. Now, overlapping photography is needed to determine parallax and stereo oblique 3D viewing, and we call them as forward overlap or end overlap. But then at the same time, we have something called as side overlap. So in case of aerial photography, it is very important. Let me again share here some more development which I have taken recently. Earlier, the entire photography was controlled by Survey of India, and Survey of India used to give this responsibility to either the Indian Air Force or to a private company stationed in Kolkata called as Basis Air Survey Company, Kolkata. And the third part was given to the NRSC, that is called as National Remote Sensing Center. Now these three organizations were doing photography for you. Now in the recent years, particularly Chandigarh has taken a lead. And in Chandigarh, we are not going to use the airplanes, we are going to use the unmanned aerial vehicles, that is called as drones. In the last week of September itself, Chandigarh administration has decided that they are going to do the photography of Sector 7 in Chandigarh for the mapping of the use of land in Sector 7. Now this is a new beginning. So in place of aerial photography, this will be aerial photography, but not use of plane will be there, there will be drones. So drone photography has been introduced. That means they are low altitude photography, where the possibility of mapping the information will be very high. That means in a high resolution. And suppose this work is to be done, friends, the simple principle of overlap has to be ensured. That is very important. And if this is not known to you, then the 3-day work will not be possible. On second point, so the first is that we have to ensure that photography is done correctly, where the overlap is very important. Second point is photographic scale. Now scale defines the relationship between a linear distance on a vertical photograph and the corresponding actual distance on the ground. Very simple. On the map, you have seen you are measuring all the horizontal distances with the help of a common scale called as representative fractions, map scale, simple words. But in case of maps, what you find, the vertical distances were not measured with this scale. Vertical distances on the map are measured with the help of contours. And contours are having a different scale as compared to the simple maps. So on a map itself, it is a topographic map, we find that it is not one scale, but you have to keep two different scales in mind. One for the measurement of horizontal distances, two for the measurement of vertical distances. In case of photograph, what we find that we have to identify both the scale, which can be used for the vertical heights as well as the linear heights. Photographic scale indicates proportional distance. Now scale expressed as a representative fraction between the linear distance on the photo and the corresponding distance on the ground will be simply the relationship between the focal length of the camera and the height of the plane, which we will be discussing. So, for example, if the scale is 1:25,000 or 1:25,000, which means that a length of 1 unit of measurement on the photo represents 25,000 units of measurement on the ground. I assume here, friends, that most of you understand the map scale. I assume here that you have a training where you can convert these scales into the statement scale or in the linear scale. That is, I assume. Now here it is very important for us to understand the difference between a small scale or a large scale. So on a small scale, what will happen? Larger denominators, objects. So on a small scale, the denominator will be large. On a large scale, we have a small denominator. So look at the values. For example, 1:1,20,000 is a small scale map. So denominator will be bigger in value. On a large scale, it is 1:10,000. Now 10,000 as a denominator is a smaller value. But what will happen? In a small scale map, objects appear small on the image. Image cover larger ground area. Number two, on a large scale, what will happen? Objects appear large on the image. Image covers a small area, small ground area. So area covered will be small, but the information available in large scale will be more. In case of small scale, suppose it's a world map. On the world map, you cannot recognize your village. It will not be there. On a world scale, on a world map, you cannot see even the rivers. Only major rivers are visible to you. So that is the concept which you have to keep in mind when you do the photography. Now look at this, friends. Now what we have photographic scale, which is the relationship between focal length and the height of the camera. Now if you look at this diagram very carefully, what you find that you learnt about from the diagram that the negative plane and the optical center, which you can see on the diagram as F. So the distance between the negative plane and the optical center is denominated here as F. But what we find that we have a capital H. Now the capital H is the optical center, and this is with reference to the mean sea level. I repeat, very important. Now every plane which flies and takes photograph has an altimeter. Now friends, the altimeter reading will give you the height of the plane with respect to mean sea level. Mean sea level. Now you are flying, suppose, in Chandigarh. Now the mean sea level height of Chandigarh is about 330 meters above mean sea level. Okay, but the plane which is flying in Chandigarh, maybe it is flying at a height of about 100 meter or 200 meters above Chandigarh. So 300 meter of the height of the Chandigarh and 200 meter of height with respect to Chandigarh will add to altimeter height. So the plane will read a height of about 500 meters. But in actual practice, it is flying at a height of about only 200 meters with respect to Chandigarh. Now this is very important that you have to work out the actual height of the plane with respect to the area in which it is flying, rather than the height which the altimeter is showing. So altimeter may show a height of about 1500 meters, but the area on which it is flying, it may be only 500 meters above the ground on which it is flying. This is very, very important for you. So what you find? So what happens? We have to subtract from the diagram the small h. Now small h is the terrain elevation with respect to the mean sea level. So from the capital H, when we subtract this, we get h dash. On the diagram it is clear. Now this h dash is nothing but the flying height of the plane with respect to the area on which it is flying. Friends, this is going to vary from place to place, but then this is the simple formula with which, so what you find, if you know the flying altitude which is given in the altimeter, you are also supposed to know the average elevation of the area on which the plane is flying, and you have to subtract it. And if you do it, then you can find out the scale of the photograph, the simple formula called as focal length upon flying altitude, that is h dash, which is called as height above terrain. Height above terrain, not height as given by the plane is altimeter height. This is very, very important, very, very important in the photographic scale. So the kind of photographs which are made available for the training purpose in India, on each photograph the photo scale can be worked out, because the focal length of the camera is printed and the altimeter reading is given, and if you know the average altitude of the place, then you can easily work it out. The focal length is given. Now this is the simple explanation of the same thing. So you can find out, so if you want to calculate the RF, that is the primitive fraction, focal length upon h dash, where f is focal length, h dash is flying height above terrain. I repeat again, this is not the altimeter reading, you have to differentiate. So if you have the focal length of 210 millimeters and height of the plane was 2500 meters, that is MSL, which is the altimeter reading, and the ground elevation is 400 meters, then what happens? 2500 meters minus 400 meters will give you a height of 2100 meters. But remember, when we have to convert the scale, the numerator and denominator should be in the same unit. So if you can see 210 millimeter was the focal length, we converted the distance or the height of the plane with respect to terrain, so it was 2100 meters, converted into millimeters, we get 21 lakh millimeters, and when we convert it, we get a scale of 1:10,000. Not a very difficult thing, but then one has to be very careful when we work out this scale. This is one simple method of calculating the photo scale. The moment you calculate the photo scale, now we have 1:10,000. What does it mean? It means that 1 unit on the map is equivalent to 10,000 unit on the ground. So suppose it is 1 centimeter on the map, then there will be 10,000 centimeter of the length of the object on the ground. Or suppose it is 1 inch, then it will be 10,000 inches, because you have to read both in the same unit so that you can convert them. If it is 1 centimeter, then the denominator will be in centimeters. If you read it in 1 inches, then the denominator will be read in 10,000 inches. This is very important when we convert it into RF. Now, sometimes what happens that the focal length is not known to you. The altimeter is also not known to you. Or sometimes what happens that you do not know the average elevation of the area, but then you have to work it out the scale. Now what happens, friends? In this situation, you have to find out with the help of simple maps. So you are supposed to have a corresponding map of the corresponding area, and then you have to find out any two known locations and their respective distances on the map. So first of all, you have to work out the actual distances on the map and the same corresponding distances on the photograph. I will demonstrate it on the board so that you can understand it very easy. This will be the second different situation where you have to work out the photo scale. Now let's look at it. So here is my photograph, and here I have a map of the same area. Now my problem is I have to work out this photo scale. Map scale is given to me. So map scale is suppose given to me, and map scale says it is 1:50,000. This is normally given on all topographic sheets. Now on this topographic sheet, I find that here is a road, and I find that here is a crossing. I find here is a crossing. Now this is how the map looks to me. Now I find that this crossing and this crossing is there, so I mark it as A here, I mark it B here. I find that I can see the same thing here on my satellite imaging or my photograph. Now what I find that this distance and this distance, they are not same. But for this I don't know the scale. I don't know the scale. But I find that yes, this is the same road, this is the same road, the roads here are same. Now suppose I measure this distance and I find it is 10 centimeter. Now I'm supposed to convert this 10 centimeter with the help of this. So when I do it, I find that this distance is about 5 kilometers. Because 1 centimeter with respect to this will give me 500 meters. Since it is 10 centimeter, this will be about 5 kilometers. I believe you understand the simple conversion. If not, then maybe sometime next I will teach you about how to convert this. 10 centimeter on this scale will represent 5 kilometers because 1 centimeter represents here 500 meters. Because 1 centimeter is equal to 5000 centimeters, which means about half a kilometer. So 1 centimeter on this map represents half a kilometer. 10 centimeter will represent 5 kilometers. So what I come to know? I come to know that the distance between A and B on my photograph will also be equal to 5 kilometers because this is the same distance which is there on the map. So with the help of this, now what I learned that this much distance is equal to 5 kilometers. Now I am going to measure this distance on the photograph. So if I measure it, I find it to be I find that it is approximately 5 centimeters. Here it was 10 centimeters. So I have 5 centimeters on the photograph representing 5 kilometers of length because I can measure this distance. Now with the help of these two relationships, the 5 centimeter represents 5 kilometers, I work out my scale. And then I find that my scale here will be 1:1 lakh rather than 1:50,000. That is how we convert it. And that makes sense that this is how we can calculate the photo scale. Very important. So what we learned that sometimes when you may say that no, it is not possible to get the focal length of the camera. I cannot get the altimeter reading. No problem. What you can do? You have to look at a corresponding map. But sometimes, friends, it is possible you don't get a map also because now we are interested in the enemy area. Don't worry, because all this is in the training mode. So then what you have to do? Then you have to use your intelligence. Here lies your intelligence. And look at it. What you can do then? Then you have to look at and use your intelligence that yes, there could be a possibility that you do not have a map, but you are using your intelligence and you find that on your photograph there is a cricket pitch visible to you. And then you know that one cricket pitch from the one corner to the other corner has a distance of about 22 yards. So the photo distance is to be measured. So when you measure this distance on the photograph, you find that this comes to about 2 centimeters. Now 2 centimeters will be equivalent to 22 yards. Now what happens? You have a known object, and the known object's distance is known to you. Now with this relationship you can also work out. So there is not one method. We have to be very, very creative. Sometimes it is possible that no, there is nothing like this on the photograph which you know about it. But then even then, don't be discouraged. There are other ways. Again, your intelligence is going to help you. So if you are familiar with the human beings, and then you can find a house somewhere, and if it is a single story building, then you have to assume that what could be the approximate height of a building in which a human being lives. A human being in a single story house will not be having 500 meters of height. Common sense says it will not be 1 centimeter height. So you know that a person in the India or across the world will have an average height of a one story building approximately about 12 to 15 meters, 12 to 15 feet, the one single, in which the door height will be approximately 7 feet. Now again, you are using your intelligence, you can find out the relationship between the actual height of an object, maybe average, very close. Now what will happen in such a situation? In such a situation, your measurement may not be very precise, but you are going to be very close to reality. So because the purpose is to calculate the photo scale, and since we have calculated the photo scale in different ways, either using the focal length and the height of the plane above the terrain, or whether you use the map, or whether you use the method of known objects, or whether you are using your intelligence and finding out what could be the possible height of a building or possible length of a car, if it is visible. possible length of a bus which is visible, and that with the help of that you can approximately calculate the photo scale and you can find out the major distances. Though it is true, it may not be very precise, but then this is the method which you can use using your intelligence. There could be many more methods which you can look at. Here what you find that effect of flying height on the ground coverage will be there. So if you look at it, what happens? When the height was different, the area coverage was big. When the height was reduced, the area coverage also reduced. Now here it is very important for you to understand that, see, when we increase the height of the plane, the area coverage will increase, and when the area coverage increases, friends, what will happen? The photo scale will become small. I repeat for you, photo scale will become small. That means details on the photograph will be less available to you. The area coverage is more, but the amount of information which you want to extract will be less. If you reduce the height, the area coverage will be less, but then the details of that area will be more, and therefore the flying height and photo scale concept should be very clear. If you want a large scale photography, you have to go for low altitude photography. If you want a small scale photography, you have to go for a high altitude photography. And that is what the scale concept will be clear. And the amount of information which you want to collect will also be there. Now look at this. In this diagram, what happens? We are not changing the flying altitude, but I am changing my focal length. And what happens, friends? You have to understand the relationship of focal length and with the area coverage. So when I increase the focal length, what happens? My area coverage is decreased. I repeat for you. When I increase the focal length of my camera, the area coverage is reduced. And when I decrease the focal length of my camera, what happens? My area coverage is increased. Now, what will be the relationship in such a situation? When I increase the focal length, I am getting a large scale photography. When I reduce the focal length, what happens? My area coverage increases and I get a small scale photography. That means now you have understood two important concepts. That your photo scale is getting changed by change in the photo scale or by change in the flying altitude. And that is very, very important for you to understand. Now this is the same thing has been explained. I can miss this. Now what do you find? Now in case of aerial photographs, altitude variation during flight will be there. Why will it be there? I explain you again with the help of a diagram, because now we have understood two basic concepts. The first concept was that flying altitude and the focal length, they are changing the photo scale. Now look at it, what I am going to discuss with you in photogrammetry is very important concept. Now friends, look at it. This is a situation of a vertical photograph. Now suppose it is a flat plane area. It is a flat plane area. Now what happens? This is my perpendicular position, that is our principal point on the ground. Now what will happen? In most scientific terms, friends, the scale on the photograph will be accurate only at my principal point. Most accurate. Why? But if I look at it, what happens when such a situation is there? Now, from here to here, the distances will be minimum. As I move away from it, distances keep on changing. Distances keep on changing. And I'll explain you this concept with a concept of projections. I'll be using the other part of it. Look at friends, what happens in the case of projections. Now suppose my source of light is here and my flat plane sheet is tangent to the pole. Okay. Now this is to be replicated here very carefully. Now what I find that if the source of light is here, if I project the pole, now pole is exactly depicted on the paper. The location of pole is correct. There is no problem. But suppose I want to project this lump of light. Now look at what happens. Now this point is getting projected here. Suppose I want to project this point. Now what happens? This point is getting projected here. And suppose I am interested in I want to project this. What I find I can't project it. Now this point cannot be projected on this projection. Now look at your school days geography, simple geography. What you find that in this situation what happens? If you are preparing a map, you cannot show the equator on the map. With this kind of projection, only polar areas can be shown and only one hemisphere is possible to show. Because the moment you go away from the pole towards the equator, the scale gets exaggerated to a very, very large extent. Now, the scale here will be exaggerated because if I want to mark this one, now look at it, this is going to be put here. Now, these distances are not equal. Whereas in your school days you will learn that if there are latitudes, the latitudes are equally spaced. Here we find that they are not equally spaced. The distance here to here, here to here, here to here, they keep on increasing. Same principle, friends, apply here when you go for the photography. Because this photography is similar to the central projection. So what you find that this optical center, when it is vertical above this point which depicted on the photograph, now the scale here will be correct. The moment you go away from this, what happens? The scale gets exaggerated. And what will happen? I'll give you an example. Suppose in this area, we have a large number of electric poles. Now on this point, this electric pole will be shown as point. This point where there is an electric pole, because the camera is vertically above it, what will happen? This electric pole will appear as a point. Now another electric pole which is here will appear you as a line. And yes, another electric pole will appear like a bigger line. And when you look at the photograph for the first time, in your mind what will happen? You will say that this is a point, this is a small pole, and this is a bigger pole. But the reality is that whether this is a dot, whether it is a small line, whether it is a big line, all of them are just poles, and poles of same dimension. And that is what we say, that our objects will get displaced. So we'll find that this is how they will appear on the. So they're all electric poles, but then the look of different dimensions. They're all electric poles. So for a common man who has no training in photogrammetry, they are going to read this photograph very differently. But for a trained person, one has to understand that this is because of the relief displacing. The objects get displaced. So what we learn from this simple photograph? We learn that as we move away from this principal point towards the periphery of the photograph, there will be an increase in the radial displacement. So the displacement is radially outward. I again repeat, displacement is radially outward. So this is very important. So what we find that it was very easy for us to seeing things on the photograph, but when it comes to the measurement part of it, one has to be very, very careful that what we see sometimes is not correct. What we see sometimes is not correct. This is very important. I move further. So this was about the relief displacement. So relief displacement is the shift in an object's image position caused by its elevation above a particular datum. For vertical or near vertical photography, the shift occurs radially from the nadir point. In this case, nadir point is nothing but your principal point, which can be calculated. This is how we calculate the relief displacement. But then time is not, so I will maybe we can stop here itself. I have explained them the basics of the photogrammetry. Friends, there are many more things, but then time does not permit me to go further. But if you have a few pointed questions, I will be very happy to answer them. Thank you very much. Thank you. Centers. I once again repeat that, see, I have given you only the elementary ABCD of the photogrammetry. For details, you have to attend some longer courses. If you have any question, I will be welcome them.
Hello,
Yes, please.
sir. I am Dr. Nandish,
Yes, Randis.
calling from SPFU Center, Bangalore.
Yes, please.
Regarding determination of the scale
Yes.
in a slope area,
Yes.
H will not be constant.
Yes.
H is going to vary.
Yes.
In that case, how to determine the H value?
See, the vertical aerial photographs,
Yeah.
when you go for it, if it is a flat plane area,
Yeah,
then there will be little problem with the scale. But if it is a hilly area,
yeah,
okay, if it is a hilly area, in that situation there will be a lot of problems.
yeah,
Now what will happen that in such a situation, the scale on the entire photograph will not be constant. Scale on the entire photograph will not be constant, and therefore what you have to do, you have to first work out the true planimetric locations of the objects. I repeat for you, you have to work out the true planimetric locations of the objects, and to do that we have again mathematical methods through which we can work out the true planimetric positions. That means this uneven terrain has to be converted in the form of a map. Uneven terrain has to be first transformed in the form of a map, 2D map, where relative locations are first transformed, and that is called as working out the true planimetric positions. So your question is very valid, but then methods are available through which we have to first work out the true planimetric position.
okay, sir.
Yes.
Second question,
Yes,
regarding second question, as
Yes,
per
please.
your experience,
right, sir.
if you want to give a report of a area of an urban area, if it
Yes.
is 5 square kilometers or a 10 square kilometers,
Yes.
how much time required to process the data of a aerial photograph?
How much
Aerial
time?
photograph. Yeah,
See, the time will depend on two factors. One, the training of the human wear.
yeah,
First will be the training of the human wear. Number two, availability of the techniques and tools with the person.
yeah,
Okay, a trained person can work out the details of an aerial photograph of a dimension of 1 kilometer by 1 kilometer, maybe in one day itself. But
Yeah.
an untrained person or an amateur person might take even a month in working out. Number one. Number two, it will depend on what kinds of details you are interested in. If you are interested in details of minutest level, then even a trained person may need more time.
No. Why I'm asking this question is,
Yes.
for a urban planning,
Yes.
one of my nearby city, we gave that project to the NRSA, or a joint project to the Survey of India.
Yes.
They took more than 2 years. They charged 10 lakhs.
There is
But if
already
we get a
service.
process data after 2 years, I cannot use the data for the at that time. So that's why I want to know how much time required, especially for urban planning applications. We need that result immediately. Number one, as you mentioned in your lecture, nowadays we are using, even in your Chandigarh regarding the drone, we
Yes.
can also nowadays we can use, but still the government is not going to give a free hand to use the drone everywhere. So
Very good.
yeah, probably they are going to implement because of the security
Yes.
purpose.
Yes.
We
Yes.
cannot use that vehicle so that
Yes.
we can get a data. And another thing is, in
Yes.
ADAS also we can use the photogrammetry suite. For
Yes.
a digital data, we can apply these photogrammetry
Yes.
techniques. But a
Yes.
aerial photograph, I
Yes.
think we need a correct information.
Yes. See, as far as your question is concerned, friends, let me tell you, three things are now in vogue. First, we have something called as a map policy, which was which started in 2005. Then we have something called as RSDP policy, that is called as remote sensing data policy, which was implemented in India in 2011. Now, the most recent development in India has taken place, that is called as Geospatial Information and Regulation Bill. I repeat, Geospatial Information and Regulation Bill,
Yeah.
which is pending in the Parliament. Now, as far as the government is concerned, security is concerned, see, the government of India is not going to give you a free hand in the use of the remote sensing or the aerial photographs at a large scale. Now, what to do in your case? Now, let me tell you, this particular lecture and this particular kind of training is meant for informing the young researchers that
Yeah,
this
yeah.
is what you can do. Okay, this is what you can do. Now,
Right.
suppose you have decided that you are interested in doing something for the government of India. Friends, each bit of information will be made to you available in the DRDO lab.
Right.
So the DRDO lab has access to everything, and they are meant for people like you who are serious and sincere about working for the country. But for a common man in the street, it is not. But then a common man in the universities or colleges, they are aware the processes involved in such kind of information. But a person working in DRDO lab, a person working in ISRO, or a person working in NRSC, or a person working in regional centers of our remote sensing centers, or a person working in a central university or a state university can procure this information, provided they give an affidavit to the government of India, particularly Ministry of Home Affairs, that the information supplied to them will be maintained in top secret situations and locations. And remember here that if this secrecy is leaked out, it is unbailable warrant. Unbailable warrant. But if you are really interested, let me tell you that every information which you need will be made available to you, provided you satisfy the Ministry of Home Affairs and the Government of India that you are going to do something for the Government of India in the highest possible secrecy.
Right.
That is what is the latest position, friends. Thank you.
Okay, sir. Thank you.
You can stop here. Somebody is interested.
Okay, good morning, all the participants at the different centers. Now we break for tea and we reassemble at 11:45. But before we break for tea, I've got a small announcement to make. I'll request all the center coordinators to kindly ensure the attendance of all the participants and the attendance sheet need to be duly signed by the coordinator and the head of the institute, and it has to be presented to this institute for any kind of reimbursement that already I've talked about. With this small announcement, we'll break for tea, and we reassemble at 11:45 for next session by Professor Ravinder Kaur, that is Introduction to GIS Systems. Thank you.
ಎಷ್ಟೊತ್ತಾಯ್ತು ಬಿಟ್ಟು 11:45 ಇವಾಗ ಬಿಟ್ಟು ಎಷ್ಟೊತ್ತಾಯ್ತು 5 minutes
This is DD SPFU. ಇದು DD. Second floor SPFU Karnataka ಅಂತ ಒಂದು ಕಾನ್ಫರೆನ್ಸ್ ಆಗಿದೆ. So they take it.
ಬ್ಯಾಗೆಲ್ಲ ಹಾಕ್ತಾರೆ ಹಿಂದಗಡೆ ಬೆಂಚ್. ಈಗ ಸೆಷನ್ ಮುಗಿದಿತ್ತು.
When she says, okay.
Good morning, friends. Good afternoon, rather. Am I audible?
Yes, madam.
Okay. So we start. Well, just to introduce myself, I am Ravinder Kaur from the Department of Geography. and I shall be speaking on geographic information systems. This is the layout of my presentation. I shall give a brief introduction. What is GIS? I shall give a description on the components of GIS, types of data, tools of GIS, GIS functional elements, and benefits of GIS, and then GIS as a multidisciplinary science. I begin. Well, GIS comprises of three words: geographical, information, and systems. Each of this word used in this technology has a meaning. When we use the word geographic, it means that this phenomena is going to deal with locations. In geography, we deal with locations, and in GIS, we work on locations. And when we work on locations, we are in fact working with relative locations and absolute locations. In GIS, we are more concerned about absolute locations. Now, absolute locations are referred in the terms of latitude and longitude. Now, this signifies the word geographic. This signifies the words information, and this signifies system. Now we ought to understand the meaning of these three terms that shall make the entire technology very clear. The idea of using the word geographic is that we are going to work on locations. In geography, you express location in terms of XY coordinates, which are known as latitudes and longitudes. Whenever we work on locations, there are two aspects which are supposed to be considered. One is absolute locations. These are absolute locations. And then we work with relative locations. Relative locations are expressed in terms of distance, time. They may be and they're always expressed in relation to some other known location. So this is clear. When we go to the second word, that is I, this stands for information. It means that we are going to work with some database. Now, over here, I would draw your attention to differentiate between data and information. When you have number of raw facts gathered together, we call them data. And when you try to cull something meaningful out of it, we call it information. Now, working in this GIS environment, we are going to work with a lot of database, trying to cull out very important and meaningful information. The word system denotes computer and its peripherals. This gives a fair good idea that you are going to use the computer as a system with hardware and software. And that is why the nomenclature GIS gives you an idea that you are going to work on geographical locations, you are going to work with database, and this database may be spatial database and attribute database. And in the we'll discuss this at length when we discuss further. And then the system word connotes that we are going to use computer and its peripherals. Now the geographical information system is a special class of information system that keeps track not only of events, activities, things, but also of where these events, activities, and things happen or exist. Word where signifies location. Geographical location is an important attribute of activities, policies, strategies, and plans. Geographical problems involve an aspect of location, either in the information used to solve them or in the solutions themselves. Now, what is GIS? GIS is a structure which contains spatial information along with its non-spatial information. Now, we need to understand these two words. What is spatial and what is non-spatial? Spatial means when you deal with geographic space, the environs around you, and most of the spatial data is in terms of latitude and longitude. GIS is a system to capture, store, and manage and analyze spatial and non-spatial information. Now, the question arises, what is non-spatial information? Non-spatial information is also called attribute information, which means that whenever you have attributes which try to explain your spatial elements or your locations, for example, if you have a location on the map which portrays any location of a city, now this latitude and longitude or these X and Y coordinates of the city become spatial information for you. But when you have a lot of data on the attributes about that city, in order to know that city better, whether it is demographic data pertaining to total population, sex ratio, workers or women participation, flora, fauna, meteorological data, and number of elements or attributes you can have. But that gives you a fair good idea of that particular location. So this data is known as non-spatial data or attribute data. Now, we also see GIS as a computerized data management system which is used to store, capture, manage, retrieve, analyze, and display spatial information along with its attribute information. Now, when we are talking about these words, capturing, storing, managing, retrieving, analyzing, these are all capabilities that a computer promises you, because we use computer as a major device, and all the inherent capabilities of a computer are offered to any user who chooses to work in GIS environment. Now, this is how one understands. These are geographical positions or locations, and we have built up information system which is based on data. And when you use geographical information, it provides the capability of integrating this information with the spatial data or geographic positions. So you have spatial database and you have attribute database. GIS will be a technology using computer hardware and software. It is going to integrate the spatial as well as non-spatial data. And when you integrate it, you are able to get some more information, and this information is used to solve the real world problems. And these days, that is why GIS is in great demand and is also used as decision support system. Your decisions shall be taken on the basis of data, and whatever decisions you take, they are going to be precise and objective, and that is why people call it decision support system. Now, coming to components of GIS. A GIS can be divided into 6 components. We have people, procedures or methods, hardware, software, data, and network. People are the viewers, they are general users, and they are GIS specialists. When we talk of procedures, these are steps taken to answer the question which needs to be resolved. When we talk of hardware, it's a computer system and its peripherals. We talk of software, there are different GIS software packages like ArcView, ArcGIS, and then we have data statistics, which are crucial to check the quality of the data before obtaining it. You have so many data sources, and when you have so many data sources, you need to use most of the data sets, but whenever you use a data set, you should be very, very careful that what are the sources from where you have acquired it and how are you using them. And when you try to combine all the above to make a system, we call it a network. Now, this is the components of GIS. When you have people, when you have hardware, you have procedures, you have data, you have software, and then you try to integrate all of them in a network, in a loop, and this is what comprises of GIS. Now we have subsystems of a GIS because GIS in itself is a huge system containing few broad subsystems. The first one is data input subsystem. Now data input subsystems includes pre-processing and transformations, data storage and retrieval, organizers for retrieval, editing, and updating. Similarly, when we talk about data manipulation and analysis, you have aggregation of the data, disaggregation of the data, and you can even go for modeling exercises. Now comes reporting. Whatever you have worked needs to be reported. This is the output where you are more concerned, and these outputs could be in tabular form, graphic form, and in most of the cases we have in the form of a map. Now we move to the next, and that is types of GIS. There are a number of geographical information systems available today. They range from high-powered analytical software to visual web applications, and each of those are used for different purposes. Due to vast number of GIS available, it is simply not possible to provide training to each individual software here. However, there are common features in all the GIS softwares. Understanding these basic features will give you confidence with any GIS system that you work in the future. And these are different types. You have web-based GIS, that means online navigation system. You have geo-browser like Google Earth, and you have desktop GIS, for example, ArcGIS. Now we come to a very, very important aspect, and that is the types of data in GIS. Because since I told you in the beginning that we are going to derive information out of the data sets, we are going to cull out the information out of the data sets, so it becomes all the more pertinent to know what kinds of data we are going to work with. Geographical information system is different from other kinds of information and therefore requires special methods to be analyzed. Here are some of the characteristics that make geographical information special. Multidimensional, at least 2 coordinates must be specified to define a location. Voluminous, a geographical database can easily reach a terabyte in size. Different representations, how is to be done and how can it strongly influence the ease of analysis at the end of the results is to be seen by a researcher or by a GIS users. It requires to understand a projection because whenever we map, we have to use a projection taking into consideration the spherical curvature of the earth, and when we draw a map, we don't take this curvature into consideration, and there are projection techniques to take care of that. We require unique analysis methods, for example, overlay, buffering. We analyze required data integration. Yes, I have been talking about, I have been emphasizing that with the help of this technology, you are able to integrate the spatial and the attribute data. And when you link the data with the help of GIS, that is the beauty of a GIS software. Data updates are expensive and they're time consuming too. Map displays require fast data retrieval. This is how we understand. We have data which can be classified into spatial and non-spatial. Spatial data further has 2 modes of representation, or You can call them as two models of spatial data. There are vector and raster. For example, we have different locations, and these locations, when they are abstracted on the map, here one needs to understand the relationship between a map, which is going to be your final output, and the GIS technology which you are going to use to create a map. All the maps we create are related to the geographical environment around us. They are supposed to be depicting the real world. But when we depict the real world, we don't depict as it is. So each map you create is an abstraction of the reality. And one must keep this into mind, because the entire philosophy of representing the data on a map is depends on it. For example, where have you to use point locations? Where have you to use line locations? Or where have you to use polygon? This all depends upon the dimensionality of the data which is under consideration. Because when you use data which is linear in form, you try to use data with symbols of lines. Because when we talk of map abstraction, this in turn follows that we abstract the objects with the help of symbols, and this entire technique is known as symbolization. And how do you portray the real world on a map is guided by the principles of symbolization, which include the consideration of dimensionality of various objects. Whether you are going to use point, whether you're going to use line, whether you're going to use polygon, shall all depend what is the dimensionality of an object which you need to show on the map. When you talk of raster, you can have continuous raster data and you can have discrete data. Raster means when you try to show data in the form of pixels. And vector is when you join the data from point to point, and whatever maps you see are all vector-based maps. Now, when coming to non-spatial data, it could be different models. You can have network data, you can have hierarchical data, and you can have relational data. Now, this is a spatial data, what it looks like. And this is a geospatial data because it is dealing with location, size, and shape of any object on planet. For example, it could be a building, it could be a lake, mountain, or even a township. Now, these are two models by which spatial data can be represented. You have raster, where you have pixels. The first diagram where you can see those square, these are the pixels. And similarly, if you're trying to show the same in the vector, it will be something which is shown in the vector layer. Because vector layer is using polygons because you're trying to deal with the aerial dimension of the data. Now coming to vector. Vector in GIS is a format which stores information about any feature of the earth in three different types of objects. Polygon, also known as regions, line, known as arc, and point. Vector structure starts and has endpoints of a line which are called nodes. Any change of direction on a line is a vertex. Lines are joined by sharing a common node. Polygons are joined when they are adjacent to each other if they share a common line. Vector objects are all created from the general graphic representation of single XY coordinates. Points are single coordinates, lines are strings of coordinates, and polygons are a closed string of coordinates, often composed of multiple lines. Now, this is how spatial data looks like. This is the diagrammatical representations of the vector data. Vector where each object is composed by a series of X and Y coordinates. You can take them in pairs also. You have points where you have single XY pair. You have lines shown on this where nodes at beginning and the end, vertices for changes in direction along a line, and polygons are closed set of lines. Spatial data, raster. Raster is the set of rows and columns that form individual cells. Each cell or a pixel has a unique data value and clearly has an area coverage proportional to the cell size. Raster cell is also known as pixel. Raster data is also known as grid data, and this represents the fourth type of features, that is surfaces. Raster data is cell-based, and this data category also includes aerial and satellite imageries. Whatever data you procure, whatever spatial data you procure from in the form of aerial photographs or satellite imageries is in form of raster format, where you can see the data in pixels. For example, in this picture, this orange is showing you the built environment, blue shows water, and this is how it has been depicted in the raster. Had it been vector, you would have different polygons for it. And the green shows the forest and the wetlands. Now coming to the types of raster data, we have continuous and discrete. An example of the discrete raster data is population density. Continuous data examples are temperature and elevation measurements. And when you have to work on these kind of data sets, which either are discrete or continuous, you can use them the way we have used it. For example, if you are showing a map of contours where elevations are being shown, this is a continuous phenomena, and it will be shown like this using different colors. And if you are trying to make a district map where you want to show population density, you can have different class intervals, you can assign different colors to it or different shades to it, and then you can make a map. Now this map would be a discrete map because there is no continuity. Now this is how we have thematic and spectral data. Thematic data is based on one theme or multiple themes. Digital elevation models, which are known as DEMs, are the best examples. The spectral data includes data captured at different wavelengths. One wavelength is suitable for few types of features, producing one data layer. Other wavelength is used for different types. You must have studied this in the remote sensing also. And when we use different data layers of different wavelengths, they combine to form one scene imaginary or an imaginary, which is formed like this, as it is clearly depicted in the diagram. I'm very sure when you must have done remote sensing, you must have covered this. Now, this is the difference between vector and raster. The raster view of the world. Suppose you are going to show the location of hotels on a map. In the central column, we have spatial entities which are supposed to be represented on the map. And in the first column, you have the raster representation, and in the last column, you have the vector representation of the same. For example, the first is the location of the hotels, and hotels would be shown by points. Now you can see in the raster, these point locations are shown as pixels, whereas the vector view of the same object is going to be points. Similarly, when we come to the representation of the lines, which are the ski lifts being shown in this, the first representation is raster when you have a row of pixels, whereas the vector view has points joined by lines. So this is a linear representation of the data. When it comes to forest, which is of course an aerial dimension, the raster representation shows number of pixels together to form an area or a forest, whereas a forest in the vector view is nothing but an area which is shown by number of points and joined them together. Look how the network of roads will appear. Similarly, similar network of roads in raster will appear as pixels in a linear form, whereas in the vector view, you will be seeing arcs and nodes. So this is how you differentiate between vector and raster. Now coming to non-spatial data, which is also known as attribute data, any attributable information related to a feature like building, construction material, building's height, building's occupancy, which can easily be recorded in tabular format and is attached to the feature when it's opened in GIS environment, is known as non-spatial or attribute data. It can also be stated as an attribute data, generally defined as additional information about each spatial feature housed in a tabular format. Now, there is a spatial data where you see number of colors, 1, 2, 3. These are different regions or areas. But when you have attributes data, this is how you will have. You can have area, you can have perimeter, you can have type. The type could be further. This could be used for a soil profile. Over here, we are trying to use a soil profile, and then we give the area and perimeter in the first instance, and then the type can be further classified, where you can have clay, silt, sand, and then you can go for sedimentation, or you can go for any number of attributes. If it would have been a geographical region, you could have gone for elements or attributes like population, population density, literacy rate, sex ratio. If it would have been a biogeographical region, you could have gone for flora and fauna species. If it was a meteorological data, you could go for temperature, pressure, wind velocity, so on and so forth. Now, the tools for GIS. We have to cull out information, as I have been emphasizing on, out of the data. And this data we acquire either from remote sensing data, or we can have geographic data in the form of maps, which are prepared by so many agencies, especially the Survey of India. You need to work on hardware, where you have a computer, a digitizer, a scanner, a printer, or a plotter. Similarly, you need to have software. You need to have desktop GIS. You can work on internet GIS. You need to have softwares, database softwares. And these days, when you are working on multimedia, you can have even 3D models. 80% of the government data collected is associated with some location in space, and we call it geographic data. If you go to the largest organization of census of India, which gives you a large gamut of attribute data, mind you, all the data is collected by locations. There may be villages, there may be towns, there may be cities, there may be million-plus cities or mega cities. There could be states, there could be tehsils, there could be talukas, and there could be village boundaries also. Similarly, information on attributes or the characteristics which you call as data can be used to symbolize, as I've told you, and provide further insight in a given location. System, of course, is a seamless operation linking this information to the geography, which requires hardware, networks, software, data, and operational procedures. And that is why you need to train yourself on a software before you use that software, and you need to learn the functioning of the software, and for that you need to have a familiarization the different modules that are available in the software. So not just the software, not just for making maps, you need to have a holistic appraisal of the entire GIS software which you intend to use. Now there are so many functional elements. The first is data acquisition. When we talk of data acquisition, we need to talk about the sources from where you will acquire data. as I've just told you, there are so many agencies from where you can acquire data. The agencies where you are going to look for spatial data are going to be very, very different. Similarly, the agencies for attribute data are numerous. It is for you to decide from where will you collect data, but before working in a GIS environment, it is for sure that you have to acquire data, and this stage is known as data acquisition. When you have acquired data as per for your requirement, then you digitize it. When you try to digitize it, you are liable of committing some mistakes, errors. When you correct them, you edit them. Then you need to build mathematical relationships of those data, which is known as topology building. You are going to use different projection transformations, and you need to understand what are projection techniques. Now, these techniques are the techniques which try to bring this spherical earth on a flat surface. So you need to know what kind of projections will be the best suited areas and for your purpose. Similarly, you have to think about pre-processing also. It could be analog to digital, or it could be conversion of units. Similarly, management would include data archival databases. That means you could have hierarchical model, network model, and relational databases, etc. Now, these databases are supposed to be managing your attribute data. Now, attribute data can be in hierarchical model, it could be networking model or relational database. When you use it in a hierarchical model, it is like parent to child relationship, and you have a hierarchy and you have hierarchical paths to reach somewhere. When they are in networking model, these data elements are going to be linked with each other. The relational database uses rows and columns, and this is the largest database model used in various softwares, because this is very easy to operate. If you want to update your data, you can. And something goes redundant, you can delete it. So relational databases are very, very important, and they're very common to the use of GIS softwares. Then you go for manipulation and analysis. These are the different capabilities of GIS softwares for spatially analyzing the data. They may be overlay, they may be buffering, connectivity operations. We are going to discuss them in detail in a few while from now. Now, these are the benefits of GIS. Once a GIS is implemented, you have numerous benefits. First of all is better maintained data. Now, better maintained data means you go for a database management system, which you call it as data DBMS. And why do you need database management system? You need database management system because you're going to work with huge sets of spatial and non-spatial data. You can have standard formats. You can have easy revisions, easy updations. You want to update your data? Create a column, create a row, and you can add the attribute information. If you find data has gone redundant, delete a row, delete a column. You can have conversion of the units, which is very easy. You can use it to search, analyze, and represent. And you have many value-added products. You enhance the productivity of the staff also. Time and money is saved. And of course, one must realize that the ultimate use or the goal of using these data sets are better decision making. GIS is a decision making tool. It is known as a decision support system. We always use GIS whenever we are to solve a problem. That is why this tool is becoming very, very popular with the government when they have to take decisions. It is becoming very, very popular with the corporate sector, and it is very, very important with even realtors these days. Whosoever is working with spatial data, this technology becomes very, very important, and it helps you to take decisions which are objective, one, precise, two. So if you want to go for an objective decision making, a precise decision making, and you want to solve the real world problems which are around you and the problems related to the real world, you can easily use these techniques and you can work in GIS environment. Now, GIS is being looked upon as a multidisciplinary science. Why? Because combination of following traditional sciences have contributed in making of this technology. Geography, yes. When you work on locations, you work with geography. If you have to portray the real world around you, if you have to look for different problems which are facing the real world, and if you're trying to find out solutions for this real world, you need to have a good geographical knowledge. Geography enables you to understand the linkages which exist on the earth, whether it is physical environment or it is human environment. Whatever problems you are trying to solve normally are the outcome of these linkages, or I must say mislinkages between the human and the physical environment. The second major contribution of geography is cartography. Cartography is art and science of making maps. The final product which you desire is a map. Unless and until you are clear with the concepts of cartography, you cannot use GIS in an effective way. So you should be having a fair good idea of the cartographic techniques which you require whenever you make maps. You should be knowing what kind of techniques you are going to use when you have to plot a point data. When can you use a linear data? When can you differentiate between different linear datas, and so on and so forth. And for this, you need to understand the art of symbolization and the art of graphic representation. You need to understand how do you make an output, map output, and how do you balance your map? Where are you going to write a title? Where shall the legend be? Because map, when you create out of GIS, it is going to communicate with the audience, with your readers. Statistics. So many statistical calculations are there. Cartography, I have already taken up. Remote sensing. This is one of the major sources of acquisition of data. Photogrammetry, computer science, operations research, mathematics, surveying, civil engineering, geodesy, environmental planning, and urban planning. So these are different multidisciplinary sciences which are using GIS as a software, as a technology to find out decisions for various problems. All these work on spatial data, and anybody working on spatial data can make use of this technology. Now, whenever we talk of GIS softwares, there are so many softwares which are available in the market. You have ISRI. ISRI is a company. You have ArcInfo, ArcView, ArcGIS. Then you have, and Idrisi is a very, very easy software to work with, and it was made by the Clark University. ILVIS is another. Integrated Land and Water Information System is another software, and there are numerous softwares. Now one must realize as what are the advantages and disadvantages of using GIS. Advantages are many. You explore both geographical and thematic components of data in a holistic way. Now what does this mean? This means that you have spatial data on one hand and you have attribute data on one hand. When you try to get, or when you try to link the spatial and the non-spatial data, there are so many combinations of the data you arrive at. And when you use GIS, it enables you to unfurl those relationships which you couldn't have understood otherwise. And when you try to unfurl a layer after layer, a layer of information, another layer of information, and then you can combine them also as an holistic way. So from part to whole and whole to part, both can be used to study different phenomena on the earth using GIS. It stresses geographical aspects of a research question. Whenever you have a research question in mind, it begins with where, what, why, how. These are questions which have a geographical input. Starting with the question of where, it becomes very, very important if you have to locate a school in a village. Now, not going by the whims and fancies of the people and trying to go for an adequate location, you can pose a question, where have you to locate a school in a village? Or if there are opportunities available in a city and you want to come up with a mall, where shall it be located? Now, these questions do not have easy answers, and you need to work on number of indicators of data, and then you are able to suggest a good site to them. Such questions are known as research questions on the locations of different phenomena, and this kind of exercise is in GIS environment is known as site suitability exercises. GIS allows handling and exploration of large volumes of data. Yes, we have been working on large volumes of data, and the tragedy was that we could never ever update that data when we were working in the conventional modes. We wanted to store that huge amount of data but did not. Now with the help of this technology, we can use this data, we can handle the data, and we can use whenever we want. And if we analyze and at some point of time that the data has gone redundant, you can delete the obsolete data and you can go for the newer ones. It allows you integration of the data from widely disparate sources. Yes, you have n number of sources for spatial data, you have n number of sources for attribute data, and this technology allows you to integrate both the spatial as well as the non-spatial data. This is the beauty of a GIS software. It allows analysis of data to explicitly incorporate location. Let me tell you, whenever you're working with GIS, one thing has to be understood in letter and spirit, that you are going to work on locations. And when you're working on locations, any problem related to location is going to be your favorite arena of working in GIS. When you're analyzing data and you are trying to explicitly understand the locations, it helps you to do that. And any problem which is related to that location becomes your focus, and GIS will definitely and certainly give you answers to your queries. It allows a wide variety of forms of visualization. These days, we are talking of 3D visualizations. We are talking of modeling exercises. And let me tell you, GIS has been very, very useful technology and a tool in doing this. We are being visited by a number of disasters. Now, it is possible for the experts to go for flood modeling. If you have to prepare and if you have to show preparedness for a disaster, and if you want to reduce the risk of a disaster at any place, you need to work out the things much in advance. And let me tell you, friends, people are going for flood modeling, and they are able to predict the floods which are going to occur in future with different permutations and combinations of the rainfall data. And then they can always be used as a guidelines when you want to prepare for the disaster risk reduction of floods in a particular area. And we are working with 3D GIS these days. we can create digital elevation models, we can just have a 3D visualization of the entire world or an area, whatever you're working on. That doesn't mean that there won't be limitations. There are limitations of GIS. Data is very, very expensive when you use in GIS. Learning curve of GIS software can be long. Yes, there are so many modules in a software, and you take a lot of time when you have to learn these softwares. Sometimes you need to have an appropriate training. You have to be adept in using this, and this curve can go very long. But once you are able to invest time, then you are able to reap the benefits also. It shows spatial relationship, but does not provide absolute solutions. Here lies the power of a thinking mind. It is going to show the spatial solutions. Yes, it will analyze the data for you, but it is for the human mind to interpret it. Sorry for interruption. Yes, I was talking about how the spatial relationships are studied, but they don't provide absolute locations. These are technologies and these are tools when you can analyze the data. You can process the data, but when it comes to interpretation, it is the human mind. It is the power of human mind. It is the expertise which comes into the way. And when you are able to add your expertise and your interpretation, then only you can reach absolute solutions. There are origins in the earth sciences and computer sciences, and solution may not be appropriate for humanities research. For social sciences, many a times which do not use the location data or the spatial data, this GIS may not be very handy. But if one realizes the power of location, then you can use this for social sciences as well. Yes. I would like to invite questions now. Am I audible? Am I audible? I think we don't have connectivity.
SPF Karnataka, Hubli.
Karwar.
Yes, sir. Do you have any query?
Yeah. Hello.
Yes, sir. Yes, sir.
Please continue with the queries. Questions, please. Am I audible?
Yes, ma'am. We don't have any query. Hello. Can you hear me, ma'am?
Yes, yes, speak out.
Yeah. We don't have any query, ma'am.
Have you followed most of the concepts?
Yeah, ma'am.
Thank you. पूछो.
SPF Karnataka. So, do you have any query?
No query, ma'am, from SPF Karnataka.
Okay. Gulbarga. Ma'am, do you have any query?
She's not audible. She's speaking something, but she's not audible.
Yes, ma'am. I'm with the Institute of Engineering and Technology right now. Do you have any query?
On करी वाले. Hello.
Yes, ma'am. Do you have any query?
Red है लगी on की off.
Ma'am, आपका mic on है, you're audible.
No, ma'am. Right now we don't have any queries.
Thank you. At Hubli, PDA College,
He wants to ask something.
yes, sir. Do you have any
Yeah,
query?
no questions from BB also.
Oh,
आप पूछिए.
Actually, I would like to differ in number of slides.
You can.
Can we have point line area using vector representation?
Point.
Representation of point line and area using vector format instead of raster format.
You can use point, line, area both in raster as well as vector.
Okay. This one
It is only the representation that matters. Point, line, area are going to be the representations of the real world. When you use them in the rasters, you use the pixel format. Whereas when you use them in the vector, they are going to be absolute points, absolute lines. That's the difference. It can be used for both. They are used for both.
How can we say that polygon and region is one and the same thing?
Yes. Polygon is a representation of a region. Region, you see, whenever we use a region, it is an aerial concept. An aerial concept is depicted in GIS by a polygon. As simple as that.
But generally when we are talking about the high level representation of areas, we say that collection of polygons or a set of polygons is defined as a region.
No, what I mean to say here is whenever you have any geographical region which has an aerial dimension, that will be represented in GIS with a polygon. Now these regions, they have a different hierarchy. They may be micro regions, they may be meso regions, and they could be macro regions.
Again, if we are talking about areas,
Regions to us means areas.
okay.
Regions, my connotation of a region is area.
But generally we say that regions are higher level object.
Yes, yes. Normally when you try to differentiate a region and an area, you try to have, it is a higher level concept because you have a level of homogeneity in a region. Over here, I do not mean to discuss in that case. For me, region means an area. And the aerial representation of any area in GIS is going through a polygon. Polygon shall represent it.
Well, can we have any example of data which is not associated with the space? Example of any GIS data which is not associated with space.
You see, whenever I use the word space, it has to be the environs. Space doesn't mean outer space, number one.
Obviously.
obviously, right? So if you are working on locations, only then the data is going to be spatial. If you are working on locations, rest of the data is all attribute.
Actually, I am confused about the definition of spatial data and non-spatial data.
Give me just 1 minute and I will just clear you. When we work on spatial data, they are essentially going to be locations, right? These locations are going to be very, very specific. Now, there cannot be two locations on the earth which will have same x and y coordinate. You see, there are places which can have same altitude, which can have same temperature, which can have same pressure, but no two places on the earth will have same location. This location makes the data so unique. This will be expressed in the terms of x and y coordinate. Now, when it is being expressed in xy coordinate, and when you are dealing with the spatial data around you, or when you deal with the real world, the entire question is to solve the problems of the real world. It is solving the problems of the real world, knowing the real world in a better way, right? The entire technology is focused on it. Now, your real world consists of spatial data. There is nothing which will not have a location in the real world. If it is a location-based phenomena, if it is a location-based query, if it is a location-based problem, GIS is the solution for it, right? So when you talk of spatial data are locations, they are connections. Connections means if there are 2 points or 2 cities on the map and you're trying to connect them through a road, it is a spatial data. So when you talk of the spatial data, when you talk of the spatiality, it is in the terms of location and connections, directions. So spatiality is expressed in terms of location, connection, and direction. Now, if there is a data set which ensures you these 3 parameters, it is a spatial data. And ultimately, it will be around a location. So if you're working on spatial data, finally, what would a spatial data look to you like? It is a map. If you are using a topo sheet of Survey of India, it is a spatial data. Then, if you are using satellite imagery, it is a spatial data. If you are using an aerial photograph, it is a spatial data. So when you are working with locations, connections, directions, distances, you are working with spatial elements. These are the spatial elements which make the concept of spatiality. Now, this is one set of data. Now, this is when you work with locations. Now, these locations have to be analyzed in terms of their attributes. Now, their attributes could be different. As per your problem, as per your understanding, as per your research project, you are going to work on different attributes. Now, these attributes, when they are linked with these spatial entities, that makes attribute data. Now, these locations and spatial, they are also known as spatial entities. And how do we represent these spatial entities on the map? On a real world, in the real world, a tree may appear to be a tree, but you can't have a tree on the map. So you have to abstract that information when you have to make a map. These spatial entities are represented. They are abstracted.
Using point length.
Yes. The whole philosophy of GIS revolves around this abstraction. Now, these point, line, and polygons are going to be the spatial entities. If you have to understand the details of or the dynamics of these spatial entities, you have to know their attributes. Now, attributes are nothing but the characteristics of these spatial entities. which will either be in the alpha or numeric. Now, when you have alphanumeric to represent these things, and you have to understand the characteristics which are very varying, you have to understand the attributes which are very varying. In fact, the entire dynamics is the varying characteristics and varying attributes of these entities. And most of the problems have to be understood in that. And since you are trying to find out a solution, keeping the locations into mind, you have to link these with these. And then you try to understand what more is required. Because when the attribute data and the spatial data are linked, you try to understand the spatial data in a much better way. And there, when you are able to understand, you are understanding the linkages, you are understanding the dynamics which these spatial entities have governed around them. Your problems could be a part of that. Suppose you take up an example. You are trying to find out. These days, people. I give you an example. The police department is interested to know. You see, which are the areas, which are the crime hotspots, right? Now, the crime hotspots means that crime is linked with a location. You need to have a spatial map of a city or a village or any district, whatever you want to work on. These are the different spatial units. So you have created a map. Now these maps will show locations. You will have police stations. You can show police stations on the map. And suppose the government is interested in order to know which are the crime hotspots on the map of the city. Now, one thing is very easy, that you go and ask people and keep asking about people which are the crime hotspots. Now, crime hotspots are nothing but those locations which will have a large amount of crime. One thing, you keep asking people, you keep asking police, and you shall reach nowhere. If you have to make a policy, if you have to make a strategy, if you have to make an intervention, you need to understand the linkages between the crime and the crime hotspot.
It would be better to use pointing polygon over the
Exactly. I'm coming to it. So you draw a map, you map all the incidences of the crime. The moment you have used point data in putting up these incidences, you will get the intensity of crime. These dots will gather at some place, and when they will gather at some place, and when they are put in together, they show that the intensity of the crime is. That is your crime hotspot, and that is what you are trying to aim at.
But that was not my question. My question remains still as it is.
Spatial data and attributed data you don't understand even now?
The definition of non-spatial data.
Non-spatial data means attribute. It reflects the characteristics. There could be n number of characteristics.
But how can we
and these characteristics are going to be description of the data, which define that data, which you are able to explain that data. These are characteristics, attributes.
But when those attributes, those characteristics, when they are describing some location, when they are describing some spatial entity, how can we say that they are non-spatial?
Not necessary that the description shall always be in terms of spatial elements. When we talk of spatial elements, it is location, it is direction, it is distance. When we talk of spatial, there are just 3 elements. Now, if you are taking these 3 elements, your spatial elements would be the same as spatial entity. But then, when you take up population, when you take up crime, when you take up flora, fauna, meteorological data, these are not spatial. These become spatial when they are attached to the location, but they are attributes in themselves. They are characteristics in themselves. This differentiates spatial and non-spatial, or attribute. All of them will be linked to spatiality because they pertain to a location, but in itself, they are not spatial unless and until they are linked to the spatial entity. When they are linked to the spatial entity, they get the concept of spatiality. Then they are interlinked. Otherwise, you just pick up the population statistics, and if you're not able to link them, those statistics will remain there. There will be just numbers. The moment you are able to link that number with a city or with a district or a taluka, then that spatiality comes into functioning.
Which are those 3?
So if you do not have any question, then we break for lunch and we reassemble at 2:30 for another session on geographical data by Mr. Mustafa.
Thank you so much.
What project you are doing?
Working on GIS conservative development.
Which guide?
ID
And therapy. You're doing it.
actually it's project. This is second year. I confirmed your
From which department? The good name?
Should I just start? A very good afternoon to all of you. I welcome you back in the post-lunch session. I'm Saeed Mustafa Kamal, and I'm a research scholar from Punjab University, Chandigarh. And today, we will discuss about the geographical data. So I'll just begin. First, the introduction. First, we'll discuss about what is a data exactly. So the data are given facts about phenomena. Data are observations made from real-world experiences organized and processed in order to make them meaningful and convert them into the information. So basically, data is all about what we observe, what we observe, and it includes how we perceive it, like how we perceive things in like in numerical form, sometime in attribute form, sometime like characteristics, the sizes, the amounts. It's sometimes countable, it's sometimes uncountable. So these all includes data. So it also includes the organization and in processed form, how we extract the information from data. So data is basically all the information we get. Like when we see a thing, like when we see towards a thing, we see all of it. But our information is that part of data which is required to be seen. For example, we look at a screen, like when we are watching a movie and we are interested in a character. So we are looking at the whole TV, and out of it, we are interested in that character. So that's the information part of the data. So when we talk about geography, it talks about the spatial characteristics. The spatial characteristics or the geographical awareness, when we talk about in historical, like in ancient times, it started with when people started inquiring where things are, where things lie. When for the first time, when people traveled, when people went around, they are actually curious about what lies around the earth, the location of resources, the location of, like in the ancient nomadic peoples, like they go in search of food. So where are things? How much of what is where is actually what geography deals about. So geographical data are facts relating to features which spatially reference to the surface. So it's spatially reference to the surface. It's what it makes like geographical. So geographical data also is simply a collection of information that can describe objects and things with relation to space. So space is an important part of geography. So in this presentation, we will try to know how the data are measured and what difficulties are involved, and try to understand what is geographical about geographical data and how we organize our data into a form suitable for analysis, and to understand what we will have to collect some data for ourselves and some data we will acquire from other sources. And the approaches to study geographical data is actually when we now our main subject would be like main theme is about remote sensing in GIS. So first of all, I'll talk about the geographical data in general, and then we'll come to the spatial aspect is a theme, as a subject, which will include data acquired through spatial remote senses, like how data is acquired through remote sensing. The remote sensing actually it came very late in geography. It's all about like 19. We started acquiring data. Technological developments. We started acquiring data in different form, in which was not there previously. And like when we talk about geographical data in general, it in its earlier times we use it as is being done in other disciplines, like and in spatial aspect, when you talk about remote sensing data, we'll include data there that are acquired through basically technology. When there were technological evolution and development, we started taking data into different forms, and it helped in particularly in geography when we study about the spatial aspect, like the remote sensing, like the data which we take when we gain from far off places. Like remote sensing is like acquiring data without being in physical contact. Particularly when we study about the Earth's surface, it is important that when we take a photograph from an aerial borne camera or a satellite, it really helps understanding geographical phenomena and processes. And also I'll describe in between, like while going through, I'll describe some instruments in geography, what the geographers use in storing or in using or in bringing the data into practice. So the learning outcomes would be to understand that data are measured in various ways, some of which are more useful than others, and not that any form of measurement is not without problems associated with error. So put geography into geographical data by considering them in the forms of geographical data matrix and link this to a spreadsheet. So spreadsheet also an instrument which geographers use to create the data matrices, how data is organized in rows and columns, and you should be able to put these ideas into practice, so that you should be actually, the end product would be how do we use these data in practice. So understanding that all data has to be collected, some data has already been collected by others for us to use. So there are different forms of data. Some data we ourselves have to collect, we have to go to the field, and some they are already available. They are available everywhere. Like we can use data which are being produced like by sometime government institutions or private or whosoever, but either individuals too, we can sometime use that too. And understand what sampling means in geographical context. Search out geographical data, physical and human, collected from secondary sources. First of all, we'll discuss about qualitative and quantitative data. So based on how we use, how will we use the data and how we acquire it, it's divided into data. Basically the geographical data or data in general is divided into qualitative and quantitative. So quantitative data are those type of information that can be measured, that can be actually quantified. It's called quantitative data. Information about quantities, so it's basically about quantities, how much, how many, like in real terms, which are like countable things. These are called quantitative. And information that can be measured and written down with numbers. So these can be expressed in numbers, like in statistics. When we use numbers, it's the quantitative data. That quantitative data imposes a relatively great amount of prior structure on collected data. Okay, sorry for the interruption. And we're talking about the amount of prior structure which is required while we use quantitative data. Like we have to, when we have to study about a phenomena or something about, like we have to structure we have to construct a study, like how and where to get the data and what sort of permutations and combination we have to use. It's required like a greater amount relatively, like relative to qualitative data. We require a much more prior structure in this in collecting the quantitative data. So a prior choice of variables with which to measure those constructs, and prior numerical categories with which to express the measured values of those variables. And quantitative data conceptually quantitative data are concerned with discovering facts about social phenomena. Like these talk about facts which assumes a fixed and measurable reality. This is what quantitative data is. And methodologically means that what methodology fundamentally it includes are like the data are collected through measuring things. So we need measurement, exact measurement, how much, like when we calculate, when we study about areas, what's the area of this in quantitative, like in units. That's what it methodologically includes. And data are measured through numerical comparison and statistical inferences. And data are reported through statistical analysis. And data at the end, it is reported through statistical analysis, not in abstract form. Like quantitative data is reported through statistical analysis. And the other form is qualitative data. So what are qualitative data? Are those type of informations that rely on other forms of portrayal and description, like information about qualities. It's a much more abstract concept. Like it doesn't have a yin and yang, like it doesn't lie as a black and white form, like what is it on. So it is portrayal and it's a description, actually how we describe things, and it's about qualities, how much, like when we talk about size, for example, like there's an interesting example when we while traveling in an aeroplane, when we saw, like if there is a desert, we can see a desert. So when we talk about that, when we say that the desert is really big, it is a qualitative data. So it's actually in an abstract form. But when we see, when some goes there and actually measures the desert, like when the area is calculated in actually numerical form, that makes it quantitative. So the qualitative, it's like information that can't actually be measured. Like we don't have any instrument to like measure it. Actually, it's not about what is the concept of how good it is. Like we can't measure goodness into something. Like we can't measure goodness, or how do you like something. Like we can't measure it. So all of these, and in these order. So qualitative data actually came later on in the subject of geography, and it's when we talk about overall disciplines, the importance of qualitative data came much later on, because previously it was not considered to be so much empirical, because so much was considered empirical. It was only in the postmodern eras, like the qualitative data is much more concentrated, and it is because it's important to focus on. For example, when we study about the gender relations, we can't most of the time bring out the truth when we use quantitative data. For example, when we study about women, for example, in some countries like Arab country, when we, for example, Saudi Arabia, maybe the woman would actually qualify to all other variables. For example, they might have good education, they might have a good amount of money earning, like they would be earning good. But when we actually see if the women are actually empowered, or they have the power in decision making, so it is not there. So it's basically the things that we can't actually count something, we can't actually bring the reality to the front using only quantitative data. So coming back to qualitative data, the construct variables and especially the measurement values from variables are determined as observation and made or even afterwards. Like over here, the observations, like whatever variables, whatever measurements, whatever description we have to give, we do it as we observe, or we do it on later on. Like interviewing is one kind of thing. When we interview someone and later on we dissect the interview, we can do it later on. Like while listening to him, we can do it later, him or her. So conceptually, the qualitative data are concerned with understanding human behavior and condition from the informant's perspective. So the informant plays a very important role, like the mediator, like the researcher who is doing it. But there's a debate about that also, like how informant's perspective are sometimes gets mixed up with whoever is responding, like whoever the subject of our research or our concern. It assumes a dynamic and negotiated reality. So it assumes it doesn't have an exact reality, like as we talk about in the quantitative data, they have a fixed reality, like it is either yes or no, like we have something. So in the qualitative data, we assume that rather a dynamic and a negotiated reality. And methodologically, data in the qualitative data are collected through participant observation in interview, and data are analyzed by themes from description by the informant, and data are reported in a language of the informant, or it is reported in an abstract form, like, and it is not in a statistical form or any other form. So geographical data matrix. Now we'll talk about, as I said, that we'll talk about some geographical instrument in which we organize or we use data, like in which the geographer uses these instruments to much more conveniently bring the data into use, utilization, or praxis. So geographers are interested in understanding the importance of location or space or place or area or region for a particular topic that they are interested in, while a sociologist might be interested in the relation between a group of people. a geographer's take on such an interest would be the influence of geographical context on the social relation. So there's a variation. So there is a different format or different methodologies involved with various disciplines. And in geography, what sociologists may be interested in studying the relation between two groups, while geographer would be interested in how geographical context, how in spatially that, like for example, a gender relation, like how is the relation between men and women. So when we talk about it, maybe the sociology would be interested in just studying the relationship between them, or as individuals or as groups, while geographers are mostly like included in spatial studies, how it varies through space, why it varies, why is this variation there. So it would be geography has its own spatial studies. So data can be located in various ways, such as coordinates. In here or like in geography, basically the data are located as coordinates, longitude, latitudes, regions, postcode, street names, and many more. The way or structure of storing these data result in the formation of geographical data matrix. Actually, when we store, our way of analyzation, the geographers, when we locate the data as according to we have like basically the data, they are mainly spatial, like they are temporal, and they are basically spatial, temporal, and non-spatial, like the attributes, like the characteristics they have. So the geographers, when we use data matrix, like the arranging data into rows and columns to analyze it in a much more, to bring it to much more practical use. And spreadsheet, when we see with a spreadsheet is, for example, where we have a spreadsheet in the Microsoft or Excel, Microsoft Office Excel. So it's an example of, it's a good example of spreadsheet. So spreadsheet are helpful and systematic ways of undertaking sometimes quite complicated routine calculations using the computer. And for example, when we see we have 5 regions or 5 variables and 5 time constant, when we studied about, we would arrange the data is like in a data matrix. What we do, how we see that we can analyze through arranging it in rows and columns, how in regions, like the variable that varies in various regions, like for example region 1, region 2, how the data varies with regions, and how regions actually itself change, or that the dynamicity, like it's a temporal data, it's a temporal relation, so how it varies with time, and how the variable itself it varies with time. So it gives the whole structure, gives us important analysis to do, important, it reflects important aspects. Now coming to geographical subfields, actually geography is basically divided into physical and human. And physical geography, when we talk about it, includes like the study of rocks and materials, landforms, soils, animals, plants, atmosphere, rivers, and other. Mainly the tangible, like there is basically a division about the tangibility and untangibility. So we mainly, like it's not a clear-cut definition, but in physical geography, we mainly study about the tangible things. And in human geography, we mainly, the studies are oriented around us human beings. So the philosophy, like in physical geography, it mostly studies about the landforms, how landforms, and when we go deeper into it, it's study about how these landforms actually, they are the dominant factor and how it decides our life. And in human geography, how it's about us, it's oriented about humans, how we impact the world around us. It studies about population, settlement, economic activities, transportation, recreational activities, religion, political systems, social traditions, human migration, agriculture, etc. And when we saw, it's the concept here to deal is with the holistic study synthesis. Like we have to, everything is related in geography. It's a basic concept of geography that everything is related to everything else. So in here we study about like everything here also it's a synthesis of all these forms of geography. Like when we study about climate change, we can't study about when we study about climate change, we don't study only about all about climate, not all about rainfall, not about the temperature changes. We also include the economic or whatever aspect is there, like other forms of. So it's an interrelationship of intergeographical like divisions, or it's a holistic when we talk generally about when we talk about recent developments, like when it's nowadays we can form like we go into we are going forward in a way that mostly believes in integration of different subjects, where like it's called multidisciplinary, or multidisciplinary. It's called, and it's coming up like nowadays area studies. Like when we see gender studies, we have departments and we have various institutions studying about gender studies, about regional study, like the international relations. When we talk about, they don't have like clear cut like discipline now discipline also are breaking up, because when we see about the division, when we talk, I'm going a bit like away from my topic, but it's important to discuss. Like previously when we talk about, when we study about the ancient scholars, they didn't had any like discipline division. They didn't have any scholar. Like when we talk about Herodotus or anyone else's like Western scholar, they didn't had any. It came very late in the academic form that we started dividing things, like it is sociology, it is geography, and it's all. But we are going into a way where things are put it up. Like for example, if I'm doing geography, a PhD in geography, and I'm like at my level, I didn't have to like, I have to look at every perspective of the discipline. Like I'm studying about gender, so I need to look about the economic aspect, social aspect, geographical aspect, everything. So this is all about it. It's all about the holistic synthesis of this. And in geographical data, when you talk about, it's about the integration of various forms of data. Like we can't have just qualitative data or quantitative data. We have to integrate both of them to get a clear picture of our problem. And when we go further, based on who is collecting the data or who is using it, the data are divided into primary and secondary. And the primary data is that which we collect ourselves, which the user itself collects. When I go to the field and talk to people, and then in that way I collect the data, that is primary data for me. So it may be, when I store it, when I write it somewhere, it may be a secondary data for someone else. If someone uses it, it's a secondary data for him. But for me, it's a primary data. And if we are a social geography, we may want to design and carry out a survey of responses, opinions about something of particular interest that I already talked about. We will have to choose the region. So it also include like sampling. When we talk about sampling, basically is taking a small unit which is a representation of the larger one. Like when we take, for example, blood samples, we don't pour all our blood. We just take a sample, and it's a representation of all the whole blood present in our body. So it is the same with when we study about some societies. We take the sampling, we study some, and by studying that, we generalize about the region or the area of study. So we will have to write and test your questions. Like we prepare some questionnaires to get into something. Like when we go to the field, we can have either questionnaires, or we can record directly in. We can do it both qualitative and quantitative way. But basically, questionnaire is an instrument of it's an instrument of conducting qualitative research, basically. So we will have to decide with whom you are going to ask your questions, and the sample size too is really important. We will have to undertake the field work to carry out the survey, first-hand information. We will have to record and code the result of the data. So the final result. This is about primary data. And talking about secondary data is whatever data which is already available for our use, which we ourselves, which the users itself or themselves, they didn't collect the data. It's called the secondary data. For example, the biggest example of it and the most important is the national population census, which every country have. Like we have in like the survey of India, they have all kind of data. Those are all secondary, and these are main source that come to mind, but where variety of data sources is staggering. And often large sample size are involved in secondary data. Often in secondary data, actually the sample sizes are large. It's study about everyone because it's been conducted mainly by some institutions. For example, we have the whole Indian survey to collect the population data. So it's done throughout India, the same size, that the same kind of data are collected throughout the whole country. So it is advantageous in many ways, especially for statistical analysis. It is also the case that large-scale microdata about individuals are becoming more and more available. This contrasts with the area-based data more usually used in geography. So in human geography, when you talk about primary data, it is basically questionnaires to interview a respondent. It's like when we have different type in human geography too. We have different methodologies to collect the primary data. Sometimes we go and just when we go to a family, when we just conduct a socioeconomic research that about the income and whatever aspect we want to study about health and income and the demography, whatever. That's also one way. But the second way is questionnaire. It's basically a qualitative research. That would be quantitative when we go and record the number of families, that are more about demographic data and about the education, for example, and health or whatever, like mortality. So that's actually the quantitative part of this primary data in human geography. And when you talk about the qualitative part, these are questionnaires. Basically questionnaires, it would include group discussions, it would include interviews. So we have different scales actually in qualitative. We have different scales in like when we interview someone, we have different scale. So scaling is one scale when we do it. Like when you ask responding to scale their response in question poll, when we say that when for example, how do you feel about the lecture, when we see that it's good or bad, very good, very bad. So they give some options, like it's a scaling. So rank, we rank sometime when we say how good was the movie. So we will say out of 10, how much would you give? So it's ranking, like out of 10, what, 6, 7, 8, 9, 10, like that. So it's and contingency, it is a closed question. So there are two types of questions, basically questionnaire. When we go and ask questions, these are open questions and closed questions. Sometimes like when we scale or when we give ranking, that or yes or no option, if you are married, yes or no, or if you like this, yes or no, that's called closed question. And the other one, we have open questions, like we give them enough space to speak about or talk about their experience. That's much more like to extract data from an open questionnaire is much more difficult than the closed one. So we usually ask for some specific detail about the characteristic of respondent who is being interviewed, and general information when we use, like these are open questions. So based on general views of the respondent, usual things like their preference for building new house in a particular region, for example. So, and secondary data in human geography, when we talk about, there are literally thousands of sources. Like we have like whatever when our national institute, like the country does, at world level, we have for example, we have the United Nations giving whole lot of data, like the subsidiaries of United Nations, like the WHO, like UNICEF, whatever they're getting. So there are a lot of data, secondary data is available to human geographers. And and all the recorded information Census of India does on decadal basis, whatever, and all the traffic data that's available, or for example, the number of four-wheelers in the city, everything which is not being collected by ourselves, which is already available there for our use, which is either being collected by an institution or an individual or whatever. So these are the secondary data in human geography. And talking about primary data in physical geography, when we talk about most of the primary data in physical geography involves going out into the field and taking measurements about the dimensions of physical environment that are of interest. So in physical geography, it's all about, like I talk about, like it's about tangible things. Like when we have to go into the field, when we have to collect a primary data in physical geography, we have to go and measure things. For example, we have to study about the like change in temperature. So we go into the field directly and measure the temperature. It's a good example. And topo sheets actually is a very fine example which geographers use, which is of great utility to the geographers, which is actually a source of primary data, because topo sheets basically are
2-dimensional or sometimes 3 basically of reality. It's actually the reality. So this is a primary data. This kind of, so we'll talk a bit about topographical sheets. So topographic map or sheet is detailed and accurate 2-dimensional representation of natural and human-made features on the Earth's surface. So these sheets are used for a number of applications. For example, we use it for camping, hunting. When we go, if we have a journal use and not for an academic purpose, we have a journal use. Like how do we use map? So, so for everything, like we use map when we for while going to camping, hunting, fishing, hiking, to urban planning, like resource management and surveying. The most distinctive characteristic of a topographical sheet is that the 3-dimensional shape of the Earth's surface is modeled by the use of contour line. So one of the distinct feature is the use of contour. Contours are really interesting. Like it represents the 3rd dimension on a 2-dimensional sphere. So basically, these are, when we define contours, these are like lines joining the places of equal heights. So when we have like when the contours line, they are of the bigger gap, so it means that the elevation it's not that steep. When the contour line are near, it means that the elevation is much more steeper. So contour lines are really important, like when you study for an instrument which shows a 3rd dimension on a 2 surface, like it shows like the variation in elevations. So contours are basically imaginary lines that connects locations of similar elevation. Contours make it possible to represent the height of mountain and steepness of slope on a 2-dimensional map surface. Okay. Is it fine? Okay. So topographic sheets also use a variety of symbols to describe both natural and human-made features such as roads, building. It's a representation of the reality, actually, the real ground surface on a 2-dimension. So it gives every kind of symbols. It uses to describe almost whatever is present in the real world. It uses the symbols to describe it, like roads, buildings, quarries, lakes, streams, vegetation, whatever is there. These symbols used to represent features can be of 3 types. It is basically on a topo sheet. It represents in point, lines, polygons. Like these instruments we also use in the GIS. Here is not about the GIS. It's about like how we do it physically. Like it's an analog data. It's not in the digital form of what we use in the GIS and remote sensing. So points are used to depict features like bridges and buildings. Lines are used to graphically illustrate features that are linear. Some common linear features include roads, railways, and rivers. So polygons for representation of areas. In the case of forested land or cleared, it's a primitive, like it's the topographical sheet is actually a primitive kind of this GIS or because we use all of these instruments, the same instrument which we used previously in construction or in the building of in the production of a topographical sheet. The same thing, like the basic concept, the same thing we use in the GIS and remote sensing, but over there's a database management system where we can easily manipulate it. Here it's in analog form. It's really tough when we compare, or when we can't compare like two things in a digital form. It's much more convenient there. So that's a way to like forward the next level of this topographical sheet, like this kind of analysis or presentation of data. So this is a topographical sheet. Basically, so it involves everything like we see here, like over here there would be contours. It's not visible. We have contours, we have symbols given in the side, so it's the controller. So over here we have features, like every feature is been described with symbols. Road and rails, for example, what kind of roads, or what kind of traffic, like traffic circles, what kind of roads, whatever is there, it's all represented in symbol form. And here we have transportation features like railways and airports, the kind of railway tracks, the kind of railway tracks on like the railway tracks, the intersection of railways and intersection of railways and roads, or airlifting, whatever there is in the real Earth, we would represent it on the map. And terrain features. This is an important, like in terrain features, we also show the 3 dimensions, like the elevations to the peaks to the slopes. And land cover, we use these polygons to represent the rectangles, squares, and and other forms of polygons to distinguish or to represent various forms of terrain features. So human activities too, we do like sports, swimming pool, where everything is represented there in the topographical map. So when we coming to the secondary data in physical geography, although it is true that there are not quite so many secondary sources that can be accessed for physical geography, there are still plenty. It is also fair to say that many useful sources for physical geography do also tend to make changes. It's like secondary sources, we don't like, there is not much in physical geography. We say it because sometimes because when we study physical geography, we tend to look mainly the primary, because when we study about changes, like for example, so we have when we have to go and see the mostly the static things. So we don't have so much of, in social processes, it's much more dynamic than the physical processes. So so in this way we say that there is not quite so many secondary sources. And the previously recorded information, maybe previously informed informations or surveys that could form a secondary data in physical geography. Now coming to the other aspect of geographical data, it is the spatial aspect, where we have this remote census data, remotely sensed data. And in here the basic the basic of the information, the basic construction of information, or the perception of information is done by an image in that data in an image form. In general terms, an image is a digital picture or representation of an object, or remotely sensed image data are digital representation of the Earth. It's actually the representation of the Earth. Image data are stored in data files, also called image files, or on magnetic tapes, the computer disk, and other form of media. The data are consist only of numbers. We record every kind of data. So it's basically an evolution to how we perceive or how we collect the data, like, and how do we manipulate it, how do we produce it. It's actually, when we generally, fundamentally, when we talk about why we collect data, it's actually to bring solutions to the real problems. And for example, through the manipulation and through more detailed study of images and the kind of information we get, we can be more like, we can bring more new and suitable solutions to our problem. For example, when we talk about for remote sensing, when we talk about it, basically for our eye, for example, it's a form of a camera, and we observe things, and when we see things, we try to bring solution to whatever is there. So it's the same with here with the remote sensing data. When we study data, for example, when here there is a flood, we study about the data. For example, previously maybe we couldn't map it out where the flood, where the impact, we can't say the territory of the impact of like the flood. But for in here, when we use the remotely sensed data, we can do it much more conveniently, or we can bring solution to the problems. So each number in the image file is a data file value. Data file values are sometimes referred to as pixels. Pixels are actually the building block of an image. The term pixel is abbreviated from picture element. A pixel is smallest part of a picture with a single value. So this is a whole other concept we will be dealing with in some other presentation, or you might have dealt with it in previous presentations. So that data file's value is measured brightness value of the pixels at a specific wavelength.
So data file value may also represent elevations. These data files what we acquired through remote sensing, and it also represent elevation. It also gives us in a like we did have an elevation representing element in the topographical sheet 2, which are the contours. Over here we can, through data, the amount of data which is being captured, or which a particular terrain reflects, or what in the a satellite captures, what a camera captures, we can also find represent elevations as is being done in digital elevation models. So it's basically the bands of data. The fundamental of the remote sensing is how do we see, for example, how do we see with our eyes? It's all what is being reflected by. We see colors, we see depth, we see brightness and darkness. It's all about what is being reflected by the the object in our observation. So image data may include several bands of information. Image data, so these data also, these are basically the instrument of this remote sensing. They use the data which is being reflected by each band. There's very, like in an electromagnetic spectrum of light, we have different bands of data. So in red, it varies. It has red, the visible band, which includes the red, green, blue, near infrared, infrared, and thermal energy. So on the basis of recording these energies or these bands, things are differentiated. Sometimes it's important to how do we differentiate between two things. So this is also like when we look to the earth, and when we study about a settlement or a forest cover area, there should be an instrument, like we should be capable of distinguishing between these two forms of where to study their extension, or when we study about the expansion of a city, or we study about deforestation, we have to distinguish between that between the various areas or various interest, or like area of interest. And primary data of other example, recording latitude and longitude through the GPS. Like it's also a form of, like when we acquire GPS when we study about locations, it's also in a form of like data that are utilizable to us. So data types in the spatial data, like in spatial, mainly spatial form, when we study about data, they are although the two terms data and information, we discussed it before, about data and information. Like information is that part of data which is required, or which is required to answer our questions or solving a problem. So data and information are often used indiscriminately. They both have a specific meaning. Data can be described as different observations which are collected and stored. Information is that data which is used in answering queries or solving a problem. Digitizing a large number of maps provide a large amount of data after hours of painstaking work, but the data can only render useful information if it's used in analysis. So it's only about the part of data information, like which is the information which is basically of our use. So basically data types in here also is spatial and non-spatial. Like spatial and non-spatial, geographic data are organized in geographic database. This database can be considered as a collection of spatially referenced data that acts as model of reality. It's all to we do it all. It's basically to create a model of reality. Model is a representation of reality, like a small, which is much more convenient to work upon, to deal with. For example, we have a model of for example, we have globe like which we use, like it's a model of the real Earth. So it is much more convenient for us to locate a place or to find a place on a globe. So models are basically the representation of, it's actually a representation of reality. So here also in remote sensing in GIS, when we talk about, we try to create a data of reality, the reality which may be in really, when we talk about in the real sense, which is much more difficult to deal with. So we create a model of the reality. So there are two basic important components of geographic database. It's the geographic position and its attribute or properties. So we have two things basically when we talk about geographic database. We have One is the location, which is geographic, which is purely geography in its nature. The second is attribute, which means the property of that thing. For example, we have things have a location to it. For example, when we talk about, like, for example, the bottle line on the table. So it has a location and it has an attribute, the shape, the color, the amount of water in there. So it's basically the attribute. So we have to study attributes are our bigger concerns, like attributes like crime is an attribute. We have bigger concern, like crime is an attribute, and we are concerned with the attribute. And spatial is where it varies over space, how it varies over space. So in other words, spatial data is about where it is it, and attribute data, what it is all, like the actual problem or where the actual thing we are studying about. So attribute data refers to the properties of spatial entities. They are often referred to as non-spatial data also, since they do not in themselves represent location information. They don't have a location in themselves. They don't represent a location. They have but a property of their own property. That's it. The quality of it, the shape of it. It's called the attribute data. So we have in this, our topic of concern is mainly the spatial data. So spatial data is the geographic position refers to the fact that each feature has a location that must be specified in a unique way. To specify the position in an absolute way, a coordinate system is used. So we basically use coordinate systems to locate something. Like, for example, we have a whole latitude and longitude drawn, imaginarily drawn on the surface of the Earth, which we locate, like every city or every village, every place on the Earth's surface have a geographical coordinate. For small areas, for example, like when we draw something on the, like in mathematics, when we do when we locate something on a piece of paper, we use simple coordinates. But for larger areas, we certainly certain accurate cartographic projections are commonly used. There are certain accurate cartographic projections. Actually, projection is actually the representation of Earth on a surface. Like project the Earth on a surface. So it requires many kind of instruments. For example, the Earth is sphere, which makes it complicated to represent the real. It's the real image on a plane surface. So for that, we use different kind of projections. For example, a different projection used for the equatorial areas or the temperate in the middle latitude. We use a different kind of coordinate, and for the polar region, we use different kind of projection. And internationally, there are many different coordinates. So we now have an internationally recognized projection coordinate systems like the UTM, Universal Transfer Mercator projection. We use it for our for a commonality of data all over that to make it more usable, to make it more exchangeable. We use a kind of similar projection internationally. And geography objects can be shown by 4 types of representation. And geographic when we talk about geographic object to locate, like when you talk about the objects on the Earth's surface, we use 4 types of representation. Why is the same as we use in the topographical sheets. It's only it's points, lines, and areas. It's basically it defines everything. What we say, when we in real thing also, when we see it, everything can be definable, either in a point or a line, whatever. For example, a bottle, a wire, a glass, or whatever. It's representable in either point, line, or area, and sometime in continuous surfaces. Like continuous surface or continuous data are a bit complicated. Like the temperature is a continuous data. You can't just put a line, draw a line.
The objects which are representable in point, lines, and areas, we use raster data mainly, which raster data. So point are simplest type of spatial data. They are 0-dimensional objects which only with only a position in a space but no length. So this is point data. And line data are basically the 1-dimensional spatial objects. Beside having a position in space, they also have a length. So line is actually 1 dimension, but they have a length. They don't have a breadth, but they have a length. So area data are 2-dimensional spatial objects which not only has a position in space and a length, but also a width. Like they have 2 dimensions. Continuous surface
when you talk about continuous surface are three-dimensional spatial object with not only a position in space and a length and width, but also a depth or height. Or when we talk about this kind of data, for I talk about the previously when I discussed about continuous surface, there's some other kind of continuous surface, but over here we have it's also the width. Okay, the depth and the height. I talked about temperature. Temperature is also a continuous data. Over here it's depth and height. Depth and height are also continuous data. How it varies, like when we study about the slope in anywhere, it's a continuous data because it never ends somewhere, because it's a regular data. It's a continuous data. So these spatial objects have not been discussed further because of most GIS do not include real volumetric spatial data. So here it is, the point, lines. How do we do it? Like a point, and we use a line, and we use this area or the polygons to represent the real Earth. So here, when we talk about it's a GIS world model and the real world. Like the real world, we divide in, while studying in GIS, we divide it into various aspects of our utilization. Like for example, we are interested in studying transportation. We digitize the transport network of the area of the region. So imagery, for example, we take image from the we take an imagery of the place. So an elevation, we can divide it to like with an elevation, because it's all a real representation. With the this GIS world model is actually, when all of these are included, this actually gives a presentation of the real world. And so it includes imagery, elevation, transportation, addresses, boundaries, water features, survey, control, like whatever my data, like whatever I have to project, like if I have to give some names, for example, to various towns in this place, so that's my data, or whatever the population of the place, that's whatever the problem you're concerned with. So, and there are many things included in this, which we actually try to, which all is a representation of the real world. When we, but sometimes we use different aspects. We choose a singular aspect of study. For example, we use transportation. For example, we use it, like we are interested in studying about transportation, so we just extract the transportation or whatever is of our utilization. So this is also a beauty of GIS world model. Like from among the real world instrument, we can study and we can bring solutions to, or we can analyze, or we can manipulate, or how do we, like when we study about transportation, that how, like where do we construct a road from, where do we construct a bridge, where would be like traffic management and everything. It could be done, it actually be more suitably done when we bring out the transportation aspect of the real Earth. Like when we bring out only the transportation relation, we can more study like it more in a much more better manner. Other concepts of spatial data. Spatial data, now we talk about the spatial data in the context of remote sensing. It is much more utilizable. Like why do we have like remote sensing? Because it has like we can like it's process and manipulate and compare data much more conveniently, or much more. We can perform actions in very fast, like. So there are many things. For example, we have linkages and matchings. So this is a property of the GIS. A GIS typically links different sets. Suppose you want to know the mortality rate to cancer among children under 10 years of age in each country. So if you want to know for example, here the example is like, if you want to know the mortality rate due to cancer among 10 years of age in each country, if you have one file that contains the number of children in this age group and another that contains the mortality rate from cancer, you must first combine. So you can combine both of these to gain for the answer, like to obtain the desired answer. So we can do it by linking these data through GIS. And exact matching we can do, like, is another form of how we can compare and the various form of data and come up with the interesting results of our concern. So exact matching occurs when you have information in one computer file about many geographical features, like for example towns, and additional information in in another file about the same set of features. So the operation to bring them together is easily achieved by using a key common to both to the files. In this case, the town's name. Thus, the record in each file with the same town name is extracted. So it's holier, like it's exact matching. So we have a key here, like for example, in here we have the town name, like the town name. So we have we can combine data, like there we have a set of data, and we have to include another property. For example, for a town, if we have every data, and now we have to include a data about the mortality rate or whatever, so we can just include it through exact matching. Like we have the key town, like adding this town, we can using the town names as a key, we can join and get like the data, the required data. Either we can connect it with the other data we have, or we can extract whatever data we are required. And hierarchical matching, it's also one kind of matching we do in GIS. So here it is actually sometimes we have different kind of data extracted. For example, employment data and whatever economic data, mainly they are done yearly. For example, in India we do it annually, but the population data we have it decadally, like in India. So we have, if we have this kind of two data for an area, like for a larger and for small areas, mainly the population is done for population survey is done for mainly small areas. So we have a data of a bigger area, and we have an area for like data for a small area. So we can actually if the data for the small area, it fits to the larger, like it fits to a part of the larger area. For example, we have a state, and in which we have a whole state data district wise, and we have a data of a district for individually. So we can match them too, like it's called the hierarchical data, is the same as them. And by adding the data to each district, like district wide of each district, we can also combine it, and we can make it them, if we can get the exact matching what we studied before, exact matching, we can do it that way. And third is a fuzzy match. Fuzzy matching is also an interesting like process which we can perform in the through the GIS. It's a utility of the GIS. We do it. Sometimes the data, they are not totally compatible. Like they are not boundary. Their boundaries are not same. For example, when we talk about fertility and soil type, like fertility and soil type, or agriculture and soil type, they doesn't always overlap over each other. But in here through GIS, we can of course overlap these kind of data and find out, like for example, in what kind of soil, how much of like a soil type is being occupied by the agriculture or whatever. So a GIS can carry out all these operations because it uses geography as a common key between the data sets. So it's all about the location, because it uses location of each, like points of common location is a key. So information linked only if it relates to the same geographical area. So it's basically geography, and information basically in all kind of GIS processes, these are being linked to a same geographical phenomena. So geography always remains the same. Thank you. Thank you very much.
Any center, would you like to ask any query? Do you have any query? Would you like to give any feedback?
Can I speak?
Yeah, sure.
If you have any queries or questions, you can just ask.
Ma'am, your mic is not working.
Hello, sir.
Hello.
Yeah, sir, we just want to know that can you share the presentation which you just presented now, like the PPT?
Yes, of course. Yes, of course. I'll give it to the concerned person here, and maybe they will share it with you.
Thank you so much, sir.
Okay, you're welcome. If you have any questions or queries, you can just ask. Please. If you have any questions or queries, you can just put up.
Good, Bhargav, you can write your query in chat box. Your mic is not working. Ma'am, you can write your query in chat box. The camera collects data in different spectrum at a time.
What is it? Will
The camera collects data in different spectrum at a time.
yes. Yes, of course. The camera basically they do capture image in basically the visible form, like whatever image we the visible band. It collects the data. For example, it ranges from 4 micro like millimeter to 7. So the camera is capable. It's capable of capturing data into that belt. So it captures basically in the basic 3 colors like blue, green, red, and it is further divided into other colors like what we called WIBGER, like violet, indigo, blue, red, orange, red. So it is basically the camera is such a remote sensing instrument which is capable of capturing data of visible in the visible band.
It seems that they probably are interested in asking whether at a time, at the same time, in different spectrums, can the camera capture all those images at the same time?
It does it at the same time, like whenever an object is produced, it at the same time capture this kind of data. Otherwise, there are some there are few other kind of remote sensing instrument which does it in a single color too. They are there, like for example. There are various kind of, for example, nowadays we use mainly for satellite images, where we don't use these colors. We use another waveband, which is much more like it's a problem with these with this low with these bands of less wavelengths. They would tend to get more reflected, or there would be a lot of data losses in here. So we tend to use the bands with longer wavelengths, so that would give us much more data, and we would get information much more clearly. So these days we are going to use we tend to use nowadays we are developing
remote sensing like instruments which could capture the microwave actually, which is the longer relative to have much more longer wavelength than the others. So that's it.
To be very specific, if this is in the white font and here is the plane,
okay.
I want to take the picture.
Okay.
This is the principal point.
Okay.
This is the vertical axis of the camera.
Okay.
The question is, naturally the plane is in motion.
Hmm.
But at the same time, Earth is also in motion.
Okay.
To be very much specific, the question is when the principal point will be exactly perpendicular to the camera vertical axis. At that point of time, will I be able to take one image or two images? Given the fact that first image I want in infrared range and the second, that is safe in the ultraviolet range.
You can actually, but what you want is what would we say? You want to do it with a single like an instrument of taking, like we can use two kind of like remote sensing instruments. We can do it simultaneously, but I don't think if we can do it single or with a single one. If we can use two instruments of isn't one. Yeah, okay. That was the question actually. Okay, maybe yeah, we can do it, but we have not from a single instrument. Like if we have a single camera or data capturing instrument, we can't do it with them. We can use two of it. Like we can use two instruments to capture different kind of data, because objects actually reflects every kind of data. Like even what we see with our naked eyes, like when we see things, it's only the visible band we see in, but the object is actually reflecting much more like rays in much more wider band than we can observe. So we can capture it actually. It depends on what kind of sensor you have.
Suppose that answers the question.
Okay, yeah, hopefully. Any other queries? Would you please ask?
You can write down your query. You are not audible. Again, you can write down your query. If we want the temperature measurement of an area, what if we want the temperature measurement of area?
What if we want the temperature measurement of an area? Okay, the question is, what if we have to measure the temperature of an area? Okay, I'll try to answer it in the way which I like in the context of what I presented just now. So we have like different temperature reflects different kind of waves. Like a very hot element would reflect other kind of waves. A temperature varies. Like a temperature, the kind of waves they reflect, the kind of energy, the band in which it reflects, it varies with the temperature. So when we capture a data, so on the basis of variation in those kind of reflected waves or energies, we can distinguish, like in a spatially when we talk about temperature variations. So it would be like a hot temperature area would reflect more energy, maybe relatively more than the area which is relatively cooler. So it depends on how the energy is being reflected. So the whole fundamental of our GIS is about capturing energies, what kind of energy or what kind of energy in what band they are reflecting we could capture. So it's about this. So we can calculate the variations. Of course, we can determine the temperature too, and we can fundamentally talk about the variation in temperatures too. I hope this answers your question.
Okay.
Thank you very much. Is there any other queries or questions you can please ask?
Okay, if there is none, thank you very much.
Okay, then thank you very much, Mr. Mustafa. And if you do not have any other question or query on this particular topic, then we close the session for the day, and we meet again on day 3 tomorrow morning at 10 o'clock sharp. Thank you very much.